Very urgent, bro.
This is your chance to dive into deep learning for free. From the very basics to building your first neural network with Rahul Thakur, a data analytics expert at Atlassian. Welcome to Newton School's live deep learning bootcamp, a beginner friendly, hands on guide that takes you step by step into the world of AI. Whether you're a student, aspiring data scientist, or looking to switch into AI ML, this live session is made for you. And remember, don't just watch, code along live. Keep your Python editor and Jupyter notebook ready and practice everything in real time. Want more challenges? Head over to Newton School Launchpad. The link is right there in the description. Get ready to dive in. Open your notebooks, load your dataset, and let's start building deep learning models with Rahul.
Hi everyone, my name is Rahul. I have 6+ years of experience in data science domain and I have worked previously in companies like Unacademy and Razorpay.
Welcome to Newton School Launchpad. So, how your brain inspired machines to think? When brain starts braining. So, if I look at an image of a cat, if the cat is upside down, if the cat is hidden, I'm still able to figure out with quite good accuracy and confidence that that is a cat, right? Even if the surrounding is blurry and all. Our brain is quite efficient in that. Now, how does it happen? So our brain consists of billions of tiny units called neurons that actually help us in doing this stuff. So let's take an example of how does a neuron look like. So a neuron basically has three main components. One is dendrites, the other is neuron body, and the last one is axon. So dendrites are basically used and responsible for getting the input from the surroundings. So let's say we watch something from our eyes. Our eyes basically are connected with these dendrites of various neurons that actually take the visual information. Similar via touch, similar via our other surroundings via tongue, right? Then there is something called neuron body that actually does the processing part of it. And finally, the processed output is sent via the axon. Now, our human body has billions and billions of neurons to help us in functioning how we work. So, let's take an example that on a very Sunday afternoon, we are basically trying to make breakfast. And by mistake, let's say we touch the pan. Okay. Now, if the pan is not hot, does it bother us? No. We don't suddenly remove the hand. But if the pan is very hot, suddenly we will remove the hand. So, what is actually happening behind the scenes? So this is like a very small example and also a hypothetical one, because one neuron is not only responsible for something, there is a bunch of neurons that are responsible. So let's say there is one neuron that is basically helpful for us in identifying whether the pan is hot or not. There is another neuron, let's say, that is connected to our visual receptors, whether it is a pan or not. And then there is a third neuron that is actually taking inputs from both these neurons and saying that it's actually a very hot pan. And when this neuron gets activated, we basically trigger a hot pan alert and we say that, listen buddy, you gotta move your hand, otherwise you're gonna get burnt, right? Similarly, same sort of inspiration was taken and we came up with the concept of single cell perceptron in the 1950s. So if you see an example over here, this is a single cell perceptron. You have bunch of inputs. There are certain things called weights, and they are basically used to process the input and give us an output. Now the formula for single cell perceptron is something like this. So here you have weights. Weights are basically to take into account how important a particular input is. So each weight is multiplied with a input W1x1, W2x2. So it's basically weighted mean. And there is a bias term. We will talk about bias in further slides. And there is a function which is known as activation function. Okay. So let's see perceptron in action. Let's say we are building a spam versus not spam classifier. So spam emails or not spam emails. Now, what could be the different types of inputs that can come to determine whether the email is spam or not. So it could be like, first input is whether the email contains the word free or not, right? So a lot of scenarios you have free, give me 500 rupees, I'll give you 1000 rupees next month. So that is a spam email, right? Then it might have some suspicious link, that is my input 2. Then it might have it be sent from an unknown address, that is input 3. And what we do is we basically assign weights to each of these inputs. So if some input is more important in determining whether a email is a spam or not, the weight will be higher. And then we'll calculate the weighted sum. And if that weighted sum, the entire value is greater than certain threshold, let's say 0.5, we'll mark it as spam, otherwise it's not a spam. So let's take this example that x1, x2, x3 were 111. So 111 basically means the email actually contained the word free, because x1 is 1. It also contained some suspicious link, that's why x2 is also 1, and it was also sent from an unknown address, so x3 is also 1. And here we have initialized w1, w2, w3 as some random values for example's sake. Ideally in Perceptron, you learn the weights via the training process. And then we'll calculate the output of this weighted sum. So 0.6 into 1, 0.6 into 1, 0.7 into 1, plus 0.2 into 1. And there is some bias also, that is 0.1 minus 1.0. The total sum comes out to be 0.5. Now, what we are saying is, if the weighted sum is greater than 0.5, or let's assume equal to 0.5, greater than equal to 0.5, then we mark it as spam. So here weighted sum came out to be 0.5. So it is greater than equals to 0.5. So it is a spam email. If the weighted sum came out to be 0.4, we would have said it is not a spam email. Now you might have noticed the term bias. So what is the role of bias term over here? The role of bias term is actually to shift the decision boundary. Decision boundary is what? That if that weighted sum w1x1 plus w2x2 plus w3x3 is greater than equals to 0.5, so it is actually creating a decision boundary, right? It's an equation, right? So it is actually creating a decision boundary. So this bias term is used to shift the decision boundary. If we don't have bias term, a decision boundary will always pass through the origin, right? So if our equation was w1x1 plus w2x2 plus w3x3 greater than equals to 0, right? We don't have a bias term, right? Y equals to mx plus 0. There is no bias. So these equations will always pass through the origin. Origin will always satisfy these equations, right? Now the problem with that is we are making our decision boundary very restrictive. And in a lot of real world scenarios, this actually does not happen. All right. So that is the reason we have to have this bias term. All right. I'll show you this with a visual example also. So let's take one more example. What is decision boundary? So understand decision boundary. We can think of it like this, that there is a cake and that cake has two sections. One has only chocolate chips, other has blueberries. And I want to cut that cake in such a way that the chocolate section is separate and blueberry section is separate, right? So the angle or the position where I'll make the cut to separate these two is actually called decision boundary. And that decision boundary is actually determined by the weights and biases of my perceptron. All right. I hope this makes sense. Now let's take as a single neuron that is making some decision. But if you take the example of hot pan, we did not use only one neuron. We had multiple neurons. We had 3 neurons in that scenario, right? So in real world, you will need multiple such neurons to make decisions, and each decision will be sent to the future neurons. And in that way, you can create complex decision boundaries. And that is where these perceptrons come. Think of perceptron as a single decision maker. It's a simple decision maker. And if I combine multiple such perceptrons, I can basically create more complex decision making systems. And this is where our deep neural network comes. Deep neural networks actually leverage these single cell perceptrons, but multiple of them to create these complex learning systems that can identify images, that can be helpful in applications like ChatGPT, right? So here is an example of a deep neural network where you have multiple of these perceptrons if you see, and each this vertical line is called a layer. We'll study layers in the next class. Each of these vertical lines are called layers, and all of them are interconnected with each other, and they will take the input, do the operation, that weighted sum plus bias, and then they will pass the output to the future or next layer neurons, and in this way we can create complex decision boundaries. But there is still one limitation in single cell perceptron. Single cell perceptron, if you saw the example of spam versus not spam, it was only useful when we had like a linear decision boundary. Linear decision boundary like a straight line or a plane, that is linear decision boundary. That problem was a linear decision boundary problem. But let's take another problem that is known as XOR problem, exclusive OR. Right, so exclusive OR, basically the output is 0 when both the values A and B, if you see the truth table of exclusive OR, if A and B are both zeros or both ones, the output of exclusive OR is 0. Otherwise it is 1. Right, so the red points over here are actually 1 and the blue points over here are actually 0. Now if I try to create any decision boundary, a straight line, if I try to create a straight line from anywhere, I will never be able to separate the red points from the blue points, right? So in this sort of scenario, we actually cannot solve this problem via perceptron. And actually there was a paper around that when this perceptron came into picture, that this is the very big limitation of perceptron, right? So to solve this part, there was something called non-linear activation functions that we'll study in our third lecture, that actually help perceptron, and they modify perceptron to create non-linear decision boundaries. All right. So in multi-layer perceptrons, basically you have multiple perceptrons. We stack perceptrons to get multiple layers of perceptrons. Then we add a non-linear activation function. It's a function that gives the ability to perceptron to learn this non-linearity, right? That case example of XOR. And then we add more and more layers for deeper understanding. And that's where deep neural network comes into picture. So this type of architecture where you have x1 and x2 were your binary bits 0, 1. You create one more layer hidden, h2, where you have two perceptrons and you have activation function also. And that basically gives you the output. This will actually help us in solving the XOR problem. Alright, how combining multiple perceptrons works, and also how forward pass happens in a multi-layer perceptron. So let us get started. So what is the architecture of multi-layer perceptron? So here is a simple multi-layer perceptron where you have 3 inputs, 1 hidden layer and 2 nodes in the final output layer, right? So it has input layer, hidden layer and output layer. That's what we have shown over here. So if you see in this example, so this is my input. I have 3 inputs. I have 3 nodes or 3 neurons in my hidden layer. This is my hidden layer and this is my final output layer. Now here we have 2 nodes in the final output layer, but you can have more than 2 also. So let's say if it was a binary classification problem, we could have 2 nodes. If it is, differentiating between cat, dog and mat, then you can have 3 nodes, right? And so on. So how many classes you have, that many nodes you will have in the final. So this is my hidden, this is my input, and this is my output layer. So in input layer also, if you had more than 3 inputs, if you had 10 inputs, 10 columns in your data frame example, right, then you would have 10 nodes open or 10 neurons. 10 nodes actually, not 10 neurons. These are not neurons, no calculation happens here. This is only demonstrating the input, right? Now let's talk about certain key concepts that we need to understand. One is layers. So what are layers? We have shown three layers over here. This is my input layer, where the input to the neural network actually takes place. This is my hidden layer, and you can have multiple hidden layers. In complex neural networks, it's not necessary that you have only one hidden layer, you could have many such layers. And this is my final output layer. Then the next part is activation functions. So if you remember in a last class, perceptron, as a plain vanilla perceptron, it cannot learn non-linear decision boundaries. For example, it failed in XOR example, right? So in order to learn more complex non-linear decision boundaries, we have a concept of activation functions. We'll talk about activation functions in further classes, but there are a lot of different variants of activation functions. Now let's talk about forward pass in multi-layer perceptron. So what is the meaning of forward pass? Forward pass basically means flowing of data through the network from left to right, that is from input to your final output, right? So this is an example of a multi-layer perceptron. Here we have 3 neurons in our input layer. It should not be neurons actually, it should be three nodes. No computation happens. Neurons, the weighted sum actually happens. No computation happens in the input layer. So this part is only 3, not neurons. In hidden layer we have 4 neurons. Here actually the computation will happen, and in the output layer also computation will happen, and we have 2 neurons. And in hidden layer we have assumed that, let's assume ReLU activation function, and in the output layer we have softmax. So let's see with an example. Here I have x1 as 1, that is first is 1, 0, and then minus 1. So let's take it over here. So I have 1, 0 and minus 1. That basically means my x1's value, okay, and my input is what? My input is 1, 0 and minus 1, right? x1 is 1, x2 is 0 and x3 is minus 1. Okay. Now how does this shape 4 by 3 happen? So basically, if you see this first, basically the connection from input to the first hidden layer, here you have 3 inputs and here you have 4 neurons, right? So this 4 by 3 matrix, so in deep learning, matrix computation happens. We calculate that weighted sum, right? That weighted sum is actually done by this matrix calculation. So this basically tells us, okay, this is the weight these values are weights for first hidden layer, these are the weights for second hidden layer, these are the weights for third hidden layer, these are the weights for fourth hidden layer. Also you remember, right, we also had the concept of biases, so that a decision boundary is not restricted to the origin, right, not passing through the origin. It could be possible, right? So here we have H1, that is for each neuron of your hidden layer, and 3 columns for each input feature, all right? And that's why you have here also, because every node over here will have one bias, so that is the reason that you have bias. This one is a bias, this one is a bias, this one is a bias, all right? That's why here the shape is 4 by 3. And now if I try to show you the calculation for, let's say, H1 node. So for H1 node, the weighted sum would be what? W1, this weight, into X1 plus W2 into X2 plus W3 into X3 plus bias 1. This is the bias 1, right? So let's do the computation. So W1 is what? 0.2. 0.2 into X1 is what? 1 plus W2 is minus 0.4. So here we can have minus 0.4 into x2, that is 0, plus W3 is 0.1 into minus 1. So this comes out to be 0.2 plus 0 into 0.4 is nothing but 0 plus minus 0.1. So the final output comes out to be 0.1, right? So this, from here you see this output arrow is coming, right, to the individual neurons of the output layer. So from here you basically got the weighted sum as 0.1. Now we have also mentioned that each hidden neuron, each layer of my hidden, each neuron of my hidden layer basically has something called ReLU activation function. Alright. Now ReLU activation function, the formula for ReLU activation function is that ReLU of any input, let's call it Z, is equal to Z if Z is greater than 0, otherwise 0 if Z is less than equals to 0. Alright. So the output is same as the same input if the number is positive, otherwise it is 0. So here ReLU of 0.1, since it's greater than 0, will be equal to 0.1, right? So the output over here from this H1 will be 0.1 here and 0.1 here also, and that will be fed to my next neuron. Same thing will happen for H2, same thing will happen for H3, same thing will happen for H4. And that's what the same operation that we did individually for H1, H2, H3, H4 can be mimicked if we call this as W1 weight. So W uppercase subscript 1 dot product of, let's call this X matrix, X plus B1. If I do this, I'll actually get before pre-activation, so weighted sum before applying the activation for all the hidden neurons. Okay, so that's what we have done over here. So these are my weights, these are my biases. This is for the output layer, we'll talk about that later on. Now you see over here, this Z uppercase 1 is actually the output before applying activation from my hidden layer 1. Here you see 0.1 is the output. We calculated for H1 as 0.1 is output, right? You can calculate for H2 also. It will be 1.1. For H3 minus 1.4, and for H4 it is 0.2, right? Then we will apply activation function before passing these values to the next layer. So the activation function of ReLU is applied. You can call ReLU as max of 0 and whatever the input is, right? So here you remember our output from H1 was actually 0.1 because it was greater than 0. So that's what 0.1, 1.1. Here it is minus 1.4, so it's negative, so output will be 0 and this will be 0. So these 0.1, 1.1, 0.0, 0.0. So from here you get 0.1, 0.1. From H2 you get 1.1, 1.1. From H3 you get 0 and 0. And from H4 you also get 0 and 0. So these will now be passed to the weights, basically passed to these neurons. And these neurons also will have weights. Here we have mentioned the weights of the next final neuron. And it will also have bias. Right? Again the same operation will happen, right? And we will get some values, the weighted W times X plus B, right? And we got over here minus 0.63 and 0.43. Now we also mentioned that the output layer has a softmax activation function. So softmax is basically used when we want to get the final output in terms of probability values, right? So here, this is the formula for softmax. We'll also dive deeper into softmax in our future classes, and they will basically, it will try to give us probability value. So here we have got 0.2576 and 0.7424. So this basically tells us that for this input, class 2 has a probability of 74%. So it has a higher chance. So in the final answer for this input might be class 2. All right. So this is the forward passing of information from left to the right of a multi-layer perceptron. Now, how does multi-layer perceptron understand or fixes the error, right? It might be possible that ideally this was actually class 1. The input should have been, classified as class 1, but the perceptron actually said it's class 2. So we'll calculate some error from our training data, and we'll start adjusting the weights and biases from right to left, and that process is known as back propagation. All right, we'll study back propagation also in future classes. So think of back propagation as something like this, that you have lot of players in there passing the ball so that we score a goal. But let's say we tried 2-3 times and we failed, right? Then what will happen is the players will adjust themselves, and they will adjust how what should be the force applied to kick the ball, so that at the end we are able to score the goal. That entire process is known as back propagation. So you have two flows of data. One is forward pass, where you take input, you calculate the hidden states values, apply activation, do it multiple times, and finally get the output. And the second flow is you take the final output and you take the real value, actual value, you calculate the error, and you start adjusting from right side to the left side the weights and biases of your neural network. This process is known as training. So there are a lot of key concepts around training. One is what is loss function, what is gradient descent, the core algorithm that helps us in adjusting these weights. Then what is back propagation? Back propagation is this entire adjustment of weights. And what is the role of learning rate? These will be taught in future classes. Now here, this is a graph where we have two weights, and we start adjusting the weights W1 and W2 in such a way that the loss or the error is as less as possible. So wherever the error is as less as possible, that is the point where we'll have to stop. This thing is achieved through an algorithm known as gradient descent. Let's take another example using the XOR use case. You remember XOR, we were failing in case of single perceptron. So here we have basically one input layer, one hidden layer, and one output layer. And in the output layer, instead of softmax, we have basically used sigmoid. Sigmoid is another activation function. That also is helpful when you want to get probability values, right? So here, neurons get activated if the weighted sum plus bias is significant enough as filtered by sigmoid. Activation function decides whether to fire the neuron, activate the neuron, or suppress it, right? Not activate that neuron. It is actually mimicking our brain, right? Certain neurons might get activated when seeing something or feeling something, right? So here the inputs are x1, x2. I have H1 neuron, H2 neuron, and then finally the output neuron. And let's say the input was 1, 0, right? So for H1, let's assume 0.5 and minus 0.6 were the weights and bias was 0.1. So we will do the weighted sum and apply the sigmoid activation function. That also converts any number into 0, between 0 to 1, something like probability. And we got some value 0.64. Same thing we will do for H2. We got some value 0.52. And these will again be passed. 0.64 and 0.52 will again be passed to my sigmoid layer, and finally we'll get some final value, right? And here we have the decision boundary for XOR case. If you remember, in single perceptron, when we were using single perceptron, we were not able to separate the blue ones from the green ones. But here you see the blue points are these, they have been classified correctly as blue, and the red points have been classified correctly as red. And you can see this color also. So the darker shades of red basically denote that the output is closer to 0, and lighter the bluish region actually denotes the output as 1. Now see this thing, if my both x1 and x2 are 0 0, the output is 0 for XOR, right? And here also we have also correctly classified as 0. If my x1 is 1, here my x2 is 1 and x1 is 0, the output is 1, and we have correctly classified as class 1 also, right? Because darker shades of blue demonstrate 1. Same thing over, and here this is darker shades of red, so this is 0. So here multi-layer perceptron is actually working correctly. How these perceptrons are arranged layer by layer to create a neural network, and we'll also go through the different types of layers that are present in neural network on a very high level. So let us get started. So what are layers in neural networks? So neural networks are basically composition of layers, and the layers are composed of perceptrons. So layers also form a building block of deep neural networks. So if you see in this diagram, this entire vertical section of blue perceptrons arranged, right? This again entire section of yellow perceptrons arranged, these green perceptrons arranged, these red perceptrons arranged. They are actually different layers of the neural network, and each layer transforms the input data into a more abstract representation. Basically, in a different dimension, it tries to transform the input data. Now, what is the anatomy of a layer? So, a layer is a set of neurons, we can call them nodes also, which are performing a transformation on the input. Each layer does the following. It takes the input vector, it applies the weights and biases that we have seen in our previous class, and then it also applies the activation function for non-linearity. And that is the output. So output is basically Wx plus B, so weights and biases applied to the input, and then that entire value that you get is passed through an activation, and that is the output. So what is the anatomy of a layer? Weights W, these are learnable parameters, right? And it is learned via the training phase, that we'll see in our next class. Bias is a constant added to the weighted sum, and activation function introduces the non-linearity. So if you have an input, there is some linear transformation. By linear transformation, we mean basically Wx plus B. So we multiply the weights and add the bias. That is a linear transformation. And then we apply the activation function, because we saw that plain perceptron cannot handle all the use cases, and it needs activation function, and then you get the output. Now, what are the different types of layers in neural networks? So you have dense layers, convolutional layers, recurrent layers, pooling layer, dropout or regularization layer, normalization layer, embedding layer. So these are quite in-depth topics. Today we are going to look into brief at a very high level around all these type of layers. So what are dense layers? So dense layers or fully connected layers, it's called fully connected also, connect every input neuron to every output neuron. So if you see, this is I have these 4 input neurons and I have a dense layer, right? So all the neurons are being connected to each and every neuron of the dense layer. You see, everything is connected to everything else. It is common in feed-forward neural network, and also it is common in final layers. So penultimate layer, it's quite common to have a dense layer. Dense layers are best for structured data. It's good for tabular data and final classification stages. So it's generally quite common to use it in final layers, basically the second last or last layer of the neural network. What are convolutional layers? So convolutional layers are actually used in cases where we are dealing with visual representation. For example, image classification. So convolutional layers are quite useful in those scenarios because images are represented as a matrix of pixel values, and each pixel value basically gives us the intensity of that particular color, right? So if you see this example, so convolutional layers extract spatial features, right? Because the pixels around an image, they have connection with each other or also along the space. So that's why it is quite useful when you want to extract spatial features. And these are also called kernels or filters. So over here, if you see, there is an input image and a kernel is applied to this input image, and there is some operation being done, and you get a feature map, right? So it might be the kernel is trying to, let's say, if I'm trying to create an image classification system, the first this kernel might be able trying to extract the outline of the shape. Maybe it's a cat, so what is the border of the cat's image, right? Different kernels are applied in a different manner to extract different spatial features from the image. So it is quite ideal for image, audio, or spatial data. Spatial data basically means where particular value, let's say in case of example, in case of this image example, uh, a pixel is having some relation with the surrounding pixels also, right? So it's related to them in space. That's why it's called spatial data. So operation over here is basically that the feature map is applied to the input patch. So every patch of this image, this kernel is applied, and you get some feature extracted from this kernel. When we will study about convolutional neural networks in detail, we'll be able to explain this in much more depth. Convolutional layers extract spatial features, and it also adds the benefit of fewer parameters. So it is basically if we don't use convolutional layer and if we use normal neural networks on images, the number of parameters will be quite high. But because this same kernel, same matrix that you see, that is being passed through our image, it is that same matrix that is passed through entire image. So we are saving upon number of parameters. Now what are recurrent layers? So recurrent layers are actually useful when you have sequential data. For example, text. So text is a classic example. If you have a problem statement of text summarization, right, or language translation, then recurrent layers are quite useful. So recurrent layers are used for sequential data where the past context is used in layers as hidden state through a gated mechanism and hidden state. So here if you see, you pass x1 to this, you get some output. Imagine this RNN unit as a neural network. Next time, that output is also passed through the same RNN again, and x2 is also passed. So you have basically what was the output from the previous time step as well as what is the current inputs word, and you again get y2, and then again it is being passed to the same neural network again with x3 as input. So you are actually giving information about what were the past words that this model has seen, as well as what is the current word that we are processing. So it is able to capture dependence, previous words dependence on the current word also. Now what are dropout layers? So if you have studied random forest, right? So over there, if you have like a lot of depth of your random forest, your model might overfit, right? Every model has ways of regularizing your process, right? So that overfitting gets reduced. So Over here also we have the concept of dropouts. So dropouts are used for regularization actually, so that our model or our deep neural network does not overfit. So if we see, dropout randomly drops neurons during training. So randomly certain neurons are switched off. That prevents overfitting and is often used in dense and convolutional neural networks. So if you have like a very high concentration of neurons, it's very high chance that your deep neural network starts memorizing the data. So dropout, what it does is it randomly switches off certain neurons during training, only during the training phase, not during the evaluation phase. And thus it also reduces the overfitting situation. Right, so this reduces the overfitting situation. So dropout layers are quite useful. If you see that your model is overfitting, you can basically use dropout layers such that so that the overfitting situation gets reduced. Now, what are pooling layers? So pooling layers are quite useful in case of images actually. Okay, so in images it tries to extract, there are different types of pooling layers, so it tries to reduce the number of features, because your images would be quite huge, right? It could be 1024 into 1024 matrix, so there are a lot of numbers. You want to extract certain important numbers from that matrix. So in those scenarios pooling layer is also quite useful. So couple of famous pooling layers are max pooling and average pooling. So what if you see over here, what is max pooling doing? It is applying the 2 by 2 matrix on this entire image, and it is getting the max value from each of the matrix. So if you see 1, 2, 5, 6, when it applies, the output is 6. 3, 4, 7, 8, the output is 8. 7, 10, 13, 14, the output over here is actually wrong, it should be 14. And 11, 12, 15, 16, the output would be 60. Now the same thing, average pooling, what it does, it basically says that whatever numbers are in my 2 by 2 matrix, I will get the average value out of them. So that is what average pooling does. So pooling layers are used to downsample the feature maps, right? So that a number of features actually gets reduced. Reduces computation, and it also helps in reducing the overfitting, and it is often used after we have applied the convolutional layer. So convolutional layer was used to extract features from the image. Now to only focus on important features, we can use max pooling or average pooling, so that our computation and overfitting gets reduced. Now what are normalization layers? So if you would have studied traditional machine learning, right? So over there, when we apply any model, we always say that it's better to normalize the features, right? So normalization of feature helps us in better convergence and faster convergence also, right? So similar to that, deep neural networks also have normalization layers. So the normalization layers are actually useful in reducing the time taken for training the model. So here you can see the example of normalization layer. So normalization layer basically in whatever is the input, it normalizes it into a certain range, right? Let's say mean as 0 and standard deviation as 1. So this will actually help the system to learn better or faster. There are two types of normalizations. One is batch normalization. So batch is what? Batch is basically you send the deep neural network, let's say 32 images at a time, okay, before you update your weights, before you update the weights. So that is called one batch, okay. Now batch normalization, what it will do is it will try to get the mean and variance, standard deviation of your entire 32 images set, and then it will try to normalize the entire batch when taking the input. This also helps in faster convergence. Now layer normalization is when you cannot pass the entire batch of data through the network. For example, layer normalization is quite important when it comes to things like RNNs. So RNNs are basically you are basically sending one word at a time in a sequence also, right? So over there batch normalization is not used, layer normalization is used. So normalization layers in deep learning, a batch is a group of samples processed together. If you have 1000 images and use a batch size of 32, the model processes 32 images at a time. So a feature is a measurable property of a single data point. So for example, let's say I have marks of different students, right? Data of different students. So they might have marks, they might have student ID, they might have age. So all of these attributes for a particular student are its features, right? In an image, features could be pixel values. In tabular data, they could be columns like age, income, etc. In a neural network layer, features usually refer to the outputs, activations from the neuron. Now, normalization layers, in case of batch normalization, each feature is normalized across the batch. So, for example, if I had age as the feature, so I will, my batch size is 32. So, what I will do is to get the mean and standard deviation to basically normalize the data, right? So, normalization is what? X minus mu upon sigma. So, I want mean and standard deviation of the data. So, for each feature, you calculate the mean and standard deviation for a particular batch. So let's say I got 32 batches, size is 32. So I'll take the 32 samples, for each feature I'll get the mean, I'll get the standard deviation, and then I will normalize the data. It is batch normalization is useful when you have large batch sizes, because your mean and standard deviation will be much more accurate. So it's quite useful in case of CNNs and fully connected layers. Layer normalization, on the other hand, is useful in case of RNNs and transformers. All features within a single sample. So in RNNs, you are passing one sentence at a time, right? So all the features within a single sample are normalized. It works well with small batch sizes or RNNs. RNNs you have one single sentence passing through the system, right? Through the neural network. So in that scenario, we have to use layer normalization. So rule of thumb, RNNs and transformers use layer normalization. Now what are embedding layers? So this will be much more intuitive when we study NLP domain. But embedding layers are basically what? Your neural network does not understand English language. It does not understand Hindi language, right? So it only understands numbers, okay? Now, we can represent the words in our language in the form of numbers. Now, those numbers, if they are created in such a way that the words that have similar meaning, their numerical representation is closer to each other, that will give the deep neural network better ability to learn the system, right? Learn the language. So here comes the concept of embedding layers. They are actually used to convert our English language or Hindi language or Kannada language words into meaningful vector representation. So, and in such a way that the words that are quite similar in meaning to each other, their vector is quite close to each other. So that is the purpose of embedding layers. So embedding layers map discrete input words to dense vectors. It understands the meaning of the words. Okay, so it converts them into numbers. There are a couple of systems or a couple of neural networks that are specifically created to create these word embeddings. One such famous NLP model or neural network model is Word2Vec, and then it is also used in transformers also. So whenever you are dealing with textual data, you would be needing embedding layers. In Keras, embedding layer class is already present, so you can use it directly. Now if you remember, perceptron had this limitation that it can only understand linear decision boundaries, right? At the end of the day, it will always create a linear decision boundary. And in real world scenarios, there are a lot of non-linear cases. So in order to tackle those non-linear cases, the concept of activation functions comes into picture. So let us get started. So how does a layer decide which neuron will activate? By neuron we mean those perceptron type of things, right, that are useful in creating deep neural networks. So if you see this example, we have input x1 and x2 and they are connected with one layer of neurons n1, n2, n3 which have their own weights and biases, right? And you remember that for each neuron we actually do that weighted sum. Now pure weighted sum will only give us linear decision boundaries, and in order to get the non-linear decision boundary, we have introduced the concept of activation functions. So if I show you over here, if you see it over here, you have x1 and you have x2, and let's say this was w1 and this is w1, and there is another weight, this, let's call this w2, right? So for each neuron, what is going to happen is w1x1 plus w2x2, this is for neuron 1, right, plus b. This summation will be calculated and that value actually is set to be z and it comes out to be 0.8. Same thing will be done for second neuron. So this will be my w1 for second neuron and this will be my w2 for second neuron, and then again the same calculation will happen. There we get z equals to 0.2, and same thing will happen for the third neuron, right? Now here we have used ReLU activation function. So ReLU activation function is basically that if the value is greater than 0, we actually say it as 1, otherwise the output is 0. So here the value is greater than 0, so it is 0.8, so the output over here will be 1, output of ReLU activation function. Here it is 0, so output will be 0, final output, and here the output will be again 1 because the z value came out to be 1.2, right? Here it is not 0.8, z value is 0.8, so the actual output from this entire neuron post activation will be 1. Here the output will be 0 and here also it will be 1. Alright. So this is one example of activation functions. So there are various types of activation functions. So let us see those. So what are the activation functions? Activation functions apply a non-linear transformation to the output of the neuron. The output basically means that weighted sum, in order to introduce the non-linearity to the neural network. So if you see, there are various types of activation functions. Without activation function, a neural network becomes a linear function. Regardless of how many layers we stack, it does not matter how deep we go, it will still be a linear function. It will be able to understand only linear data or linear classification boundaries. So now let's see different activation functions and their properties. So the various properties of activation functions are, first, they are non-linear in nature. They should be differentiable. The reason for differentiability will be addressed in the next class when we talk about optimizers. Basically, when we try to update or learn the weights, right, at the end of the day in neural network we are learning the weights, right, that is important of each input, and in order to do that we basically differentiate, and that's the reason the activation functions will also be differentiated, and we need the activation functions to be differentiable at each and every point. It should be computationally efficient. It should not be very computationally expensive process, because we have, imagine you have so many layers and so many neurons, and every neuron has activation function. So computing that also takes time. It should be bounded in nature. So it should be having some lower limit and some upper limit. It's generally desirable. And it should be monotonic. So by monotonic we mean either it's continuously increasing function or continuously decreasing function. It should not change the directions. If it changes the directions, the problem happens is that training of the model becomes a bit trickier. Now let's talk about the first activation function, that is known as sigmoid activation function. So the sigmoid activation function formula is that here the z is actually what? Z is our weighted sum. So whatever the weighted sum we get, we apply it to this function 1 upon 1 plus e to the power minus z, and that is my output. So if we plot sigmoid activation function for different values of z, you will basically get something like this sort of curve. And you can see some on over here, this part, when you are very far apart on the left side or very far apart on the right side, the slope of sigmoid activation function is almost tending to 0. This is actually known as vanishing gradient. So when we'll study again optimizers and in back propagation, vanishing gradient comes into picture, and that basically creates issues because we will be having difficulty in training the model. Its output is bounded between 0 to 1, and that is why a lot of times if you want to do classification sort of task, like whether the image is of cat or dog, right, whether the review is positive or negative. So in those sort of scenarios, you might like to have like the final layer as sigmoid layer. That helps us in getting a value something like probability. That if probability is greater than 0.5, I am saying that it's a cat image, otherwise it's a dog image. The derivative of sigmoid is basically sigmoid of z into 1 minus sigmoid of z. So the benefit of this sigmoid is its gradients are quite smooth and the output is always between 0 to 1. The problem with sigmoid is it suffers from this vanishing gradient that I told you, right? Towards the extreme left or extreme right, the slope of this curve will be almost 0, right? So it basically makes difficult to learn, to train deep neural networks. And it is not centered around 0. We ideally want the output of our activation functions to be centered around 0. That basically means if I calculate that activation function's value for various different inputs, the mean of the input should be 0. The benefit of it is that the training time reduces. Otherwise, we will take much more steps to train our system or train a deep neural network. Then the next one is tan h or hyperbolic tangent function. So the formula for hyperbolic tangent function is that z again here is the weighted sum is e to the power z minus e to the power minus z upon e to the power z plus e to the power minus z. Its output is bounded between minus 1 to 1. Right, now if you compare between sigmoid and tan h, the benefit of tan h is it is centered around 0, right? It is centered around 0, but it still suffers if you go to the extreme right, very right or very left. Its slope will almost be tending to 0. And the derivative of tan h function is 1 minus tan h square. The pros of tan h is it is 0 centered and it has stronger gradients. By gradients I mean the slope, because we will be using the slopes to update our weights during the training process. The con of this tan h is that it still suffers from vanishing gradient, right? Because it is tapering. Like if you see, it is a S short sort of shape, and towards the rightmost and towards the leftmost, the slope almost becomes 0. Now, in order to solve the issue of vanishing gradient, a new sort of activation function came into picture that's quite popular. It's known as rectified linear unit that we saw before also. Now, this is the formula for rectified linear unit, that is its value is max of 0 or z. So if z is positive, the value is z, otherwise the value is 0. Right? So the benefit of it is that towards the positive side, we don't suffer from vanishing gradient. But towards the negative side, actually we still suffer from vanishing gradient. Another benefit of this is it's very easy to compute. And the derivative of it is very easy, right? It's either 1 if z is greater than 0, otherwise it is 0. So it's very computationally efficient because we will be doing the derivative of the activation a lot of times, right? It mitigates vanishing gradient a lot, but it still suffers from vanishing gradient towards the negative side, and that is known as dying ReLU problem. Basically, you will not get any value. It will always be 0 if the weighted sum basically comes out to be 0 or less than 0. So in order to solve the dying ReLU problem, another variant of ReLU came into picture, that is known as leaky ReLU, where instead of having for negative cases the value as 0, it is alpha times z. Alpha times z, where alpha is a small number like 0.001 or 0.01, such that I still have some values that are non-negative when the values are basically that are non-zeros actually, because in ReLU I was getting 0 values. So if you see, there is still some small activation that happens in case of leaky ReLU. The derivative of leaky ReLU is also quite straightforward. It is either 1 if z is greater than 0, otherwise it is alpha. It fixes the dying ReLU issue. The only benefit of it is, right? Then there is something called parametric ReLU, where instead of fixing the alpha part that we fixed at 0.01 or 0.001, this alpha is also learned via the model during the training phase. So the benefit is that it has the ability to adjust the alpha, but it also increases the computation, right? Because we now need to learn not only the weights of the model, weights and biases, now we also need to learn this alpha part, right? Then there is another variant of ReLU that is known as exponential linear unit. So the formula for LU, it is called LU, is Fz is equals to Z if Z greater than 0. If it's positive, the output is directly Z. Otherwise, it is alpha times e to the power Z minus 1 for negative. So it actually combines ReLU and also has smooth negative saturation. There is a smoothness. If you remember, ReLU had like a, it was non-differentiable at 0. Leaky ReLU was also non-differentiable at 0, right? There was some like a tight corner that was occurring, right? But in exponential linear unit, that actually becomes smooth. It is not exactly 0 centered, but it is quite closer to 0 centered compared to the different previous versions of the ReLU that we have seen. Then there is something called swish activation. So the formula for swish activation is Z times sigmoid of Z. So the shape comes something like this. It is empirically seen that it is better than ReLU on very, very deep networks. Then there is something called GELU, Gaussian error linear unit. It's quite popular in transformers. By transformers, I mean if you have used ChatGPT, you have basically used transformers. So the formula for GELU is Fz is equals to Z times the CDF of the Gaussian of Z. It is quite useful in BERT and transformer models. Its approximate formula is given by this complex formula. Okay. GELU is smoother and approximates probabilistic gating, and it is, you can think of it like a higher version of the swish linear unit. Now here we have a comparison table for all the activation functions. See, the famous activation functions that are generally asked in interviews are sigmoid, tanh, relu and leaky relu. And if you have mentioned transformers on the resume, then probably GELU might be asked. And here we have whether it has a fixed range, whether it has some derivative, like it should be differentiable. Does it suffer from vanishing gradient? So sigmoid, tanh and relu actually suffer from vanishing gradient. Is it zero centered? So sigmoid is not zero centered, tanh is zero centered, and remaining are also not so zero centered, and all of them introduce non-linearity. So how do you choose the right activation function? So there are certain rule of thumb. So if you have like hidden layers, you will, it's generally preferred to use relu or leaky relu. If you have binary classification output, basically when you have to classify between two objects, cat versus dog, male versus female, then you will use sigmoid as an activation function in the last layer. If the network is not so deep, you can use tanh. And if you have something like a transformer, then you use swish or GELU. And for small networks, I don't think the choice actually matters. So BERT uses GELU. CNN basically use ReLU or leaky ReLU, convolutional neural networks. RNNs are historically found to be useful when you use tanh or sigmoid. So what are optimizers? So in our neural networks, we had these weights and biases that I told you that are actually adjusted so that our predicted value becomes very close to the actual value from the training data set. Right? Now, to adjust these weights and biases are also known as parameters of a deep neural network. To adjust these weights and biases, the concept of optimizer comes into picture. They actually help us in doing the real training or learning from the data. So optimizers update weights to minimize the loss function. Loss function is basically how it is calculating how far apart my predicted output is with the actual output. So they use gradients computed by back propagation. So if you remember, if I show you this example of a deep neural network, right? So if you see over here, I have these W1, W2 till W6 and B1, B2 and B3. These are the parameters of our neural network. Now we want to adjust these parameters. So what is basically going to happen is, let's say I had certain values of x1 and x2. I had certain rows, right? Let's say 1, 0, 0, 1, 0, 0 and 1 and 1. Right, so let's say I had these values and the target was when it is 1 0, the output is 1, here also the output is 1, here the output is 0, here also the output is 0. Now let's say initially we have some random values for weights and biases, okay, and y hat is basically the predicted value, y is my actual value. So let's say here the value came out to be 0, here the value came out to be 1, here the value came out to be 1, here value came out to be 0, right? Now these two are different values. I want my y hat to be exactly equal to 1, right? But it is actually coming 0, so there is a large difference. Here there is no difference, so it's correct. Here there is the difference. Here there is no difference, so it is correct, right? So what is basically going to happen is, these values y hat I got when I passed x1 as 1 and x2 as 0, and basically I got y hat as 0 in the final output from my neural network. Now what is going to happen is, we'll calculate loss. Loss basically tells us how far apart how far or close I am to my actual value. So here I am quite far. right? Here I am close, right? I am exactly close. Here again I am very far. Here I am exactly close. So what is going to happen is this getting the prediction by passing the input values, the x1, x2 values through the neural network is known as forward pass. Now what is going to happen is we'll calculate from this y hat and my actual y the loss, and that loss will be used from right to left, and these weights and biases will actually be adjusted in order to reduce this loss. This part is known as back propagation, and during back propagation only the optimizers come into picture. So that's what is mentioned over here by the term back propagation. Now here is an example of loss. What is the loss at different values of weight? This weight is called general weight, but ideally we'll plot, okay, what is the loss with different values of W5, what is the loss with different values of W6, with B3, with B1, with B2, right? And we might get something like this sort of curve, right? Now if you see this part is actually having the minimum value of loss, right? So here we are very close to our actual predictions, so we would try to come to this point to get this weight, and that is the objective of our optimizers. All right. So how does this optimization happen? So here we have taken a general parameter theta. This could be any weight, any bias, and we have taken the loss function, right? So this is basically calculating the loss when the value of theta is something. So the updated weight will be equal to the previous value of theta minus learning rate times the slope of the loss function with respect to theta. So let me come over here and explain it in a much better way. So here I have written this equation: weight new is equal to weight old minus learning rate times dl by dw old. So this dw old could be in, let's say I am talking about w5, weight 5. So weight 5, the new value of weight 5 will be equal to the old value of weight 5 minus the learning rate times dl, the loss, the loss. We'll study about various ways of computing the loss in future classes, divided by not divided by dl by dw5 volt, basically the slope. So what is the meaning of this? So let me come over here. This is also known as update rule. This is actual updation that happens in our neural network. So let's say that I tried to plot, let me plot it like this. Right. So this is, let's say, W5 axis, and here I am plotting my loss. All right, and my loss came out to be something like this. Right. So here somewhere at this point, the value of loss for W5 at this value, W5, let's call it dash, this value of W5 dash, the loss is minimum. So I want to reach this point, right? So let's say I told you, right, initially we start with a random value. So let's say initially the value of loss was somewhere over here, right? And here I had some value of, let's call it W5 dash dash, right? So W5, from W5 dash dash I want to reach this part. So in that the slope actually comes into picture. Why the slope is used? Think of it like this. At this point the slope is positive, right? So if I am subtracting from W5, this thing will come out to be positive, and this learning rate is always positive number. It is between 0 to 1. So I am subtracting a positive number from W5. That basically means I am trying to shift it towards this side, right? And that's what actually we want to do, because the minima is to the left side. Now let's think if I was somewhere over here, right? Let's call it W5 triple dash. If I was over here and I get the slope at this point, the slope will come out to be negative. This is a negative slope. So if I'm subtracting a negative number, dl by dw5 will be negative. So if I'm subtracting a negative number from w5, what is going to happen? I'm actually adding something. So it will come to it will shift to the right side, right? And that is why this equation is used. All right. So this is the core concept of gradient descent, and this will happen for each and every parameter. All right. So that's what this delta symbol signifies, the rate of change of loss with respect to a particular parameter theta. Theta could be W1, W2, W3, W4, W5. And this term is known as learning rate, and this is gradient of loss with respect to the parameter. So here we have basically this. Now gradient descent can be further categorized into three categories based on how much data you take before making the changes to your weights. So if you take one like entire data set to update your weights, basically what do we mean by entire data set? Let's say I have this thing, right? I have four samples. I pass my first sample, I calculate the loss, right? So let's call the loss for first sample as L1. Then for second sample, I again pass it and I calculate the loss. For the third sample, I again pass it and I calculate the loss. And fourth sample, I again pass it and calculate the loss, L4. Then I sum up all the losses to get the final loss. So final loss is basically sum of the losses, I equals to 1 till 4, right? And then I get and then I use this equation on the summed loss to update the weights. That basically means I am using the entire data set to update my weight once, right? I hope this part is clear. This is one, that is you are using entire data set. This thing is known as batch gradient descent. This is known as batch gradient descent. Now on the other hand, if I am updating my weights at each and every sample, basically I get my L1 loss by passing sample 1 and I start updating the weight. Then I pass sample 2 and I get L2 loss, again update the weights. Then I pass L3, again update the weights. Pass L4, again update the weights. This example is one example at a time. We are using one example at a time to update the weights, right? This is known as stochastic gradient descent. So in batch gradient descent, you are passing all the data. After all the data has been passed, you get the loss, you get the sum of it or average of it, and then you update the weights once. That is known as batch gradient descent. In stochastic gradient descent, after passing of each sample, you are updating the weights. This is known as stochastic. Now mini batch is actually somewhere in between, right? So in mini batch, instead of passing updating the weights at each sample, maybe you say that okay, after every 2 sample I will update the weight. So you pass the first row, you got the loss 1, you pass the second row, you got the loss 2, you get the average of it, and then you update the weight. This is known as mini batch gradient descent. Alright. Now why do we have these three variants? See, batch gradient descent might not be computationally possible if you have lot of rows, right? You will have to first accumulate the losses and then do the update, and it is more memory intensive. Stochastic gradient descent is not memory intensive, right? Because it is updating after each pass of your data. But the problem with stochastic is because you are making so frequent changes, the gradient might, the gradient descent algorithm will be subjected to very noisy updates, right? The benefit of both, that is you're saving memory as well as you are trying to smoothen the gradient descent, comes with mini batch gradient descent. Alright. So gradient descent is simple and powerful optimization technique, but gradient descent is slow in convergence, noisy and sensitive to the learning rate, right? If you remember, we had this learning rate also, right? This learning rate term. This learning rate also is very crucial. If you have a very high learning rate, you might never be able to learn or reach this minima point. And if you have a very low learning rate, you will take so many steps to come to this minima. It will be lot more computations involved. So having the ideal value of learning rate is also important, right? So here is a comparison table of batch gradient descent, stochastic and mini batch. So data per update, all data is required in batch, one sample is required in stochastic, and a small size of batch, let's say 3, 4, 16 is required for mini batch. The speed of convergence, how fast it converges, because it takes entire data, it is slower. Convergence basically means reaching that minima point, getting the ideal value of the weights, right? In stochastic, it is fast because every time we are updating it, the weights, so it's going to reach the minima faster. And in mini batch, it is somewhere between. Noise in updates, right? Because we are taking all the data, right? So it is less sensitive to noisy updates. Stochastic is quite sensitive, right? Very high sensitive, and mini batch is somewhere in the middle. Memory requirements, obviously batch will be very high, stochastic will be low, and mini batch is medium. Basically it depends on the size that you have mentioned. Convergence stability, basically how stable the convergence is. Batch is stable, stochastic is unstable, and mini batch is relatively stable. And in practice, almost always mini batch is used. All right. Now let's come to the challenges with our standard gradient descent. By standard gradient descent, I mean this equation. What are the challenges? See, first challenge that I mentioned is learning rate, right? We have to define the learning rate in gradient descent, and if a learning rate is not either too low or too high, we have problem. Now the second thing is you have different weights, right? W1, W2, W5, right? Your loss function will be here we basically had only, we drew the graph in using only W5 as a dimension, right? But in real world, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. So the loss will actually be dependent on those 9 parameters, right? Because those 9 parameters can change. So you will have like a multi-dimensional plot, correct? Now it might be possible that you might want separate learning rates for different dimensions, right? So that is not possible in our standard gradient descent. Third point is it might be stuck in local minima. By local minima, so let's say I had the same thing. I had my W5 and I plotted my loss function with respect to W5 and it came something like this. Something like this, right? So here also if you see, here the slope is 0, right? If my slope is 0, will my weights change over it? It will not change, right? So if by mistake, if I initialize somewhere over here and I use gradient descent, I will be stuck over here. So this is local minima. But global minima is somewhere over here. So I will be stuck in local minima and I will not get the best performance. I will get suboptimal performance. Now the next point, a very important point is saddle points. So in saddle points, gradient is 0, but it is neither local minima or local maxima. So I have, let's take a look. So here basically, this is my loss with respect to, imagine this is W1 and W2. Loss with respect to 2 parameters. Let's assume we had only 2 parameters. So local minima would be looking something like this. So let's say I started from somewhere, let me change color. Let's say I started from somewhere, I start going downwards, right? Global minima or local maxima, this is local minima, right? Local maxima is something like this. So if I start somewhere over here, I'll have to go this side, right? This is also fine. But the problem occurs with saddle points. Here I have basically loss with respect to W1 and W2. But if I say, let's say I reach somewhere over here. If I see with respect to W1, if I just plot with respect to W1 this graph, it will look something like this actually. With respect to W1, if you see, the graph is something like this. But if I plot with respect to W2, so this is W1, with respect to W2, so this is my W2 axis, it will come something like this with respect to W2. And at this point, the slope is 0 from here also with respect to here also. But ideally, it's not the point of minimum loss actually, if you see, right? The point of minimum loss might be somewhere over here. I have to start moving here. But because the slope has become 0, my gradient descent will stop. So this, it's called saddle point, because if you think of like a horse, right, you use saddle on which you sit, right? It has, like, if you see in along horizontal direction, the saddle is shaped like this. But if you see along the vertical direction of the saddle, it is actually shaped like this, right? That's why it's called saddle point. So here the slope actually becomes 0, but it's actually not a local minimum, right? It's not a minimum point. So a lot of times the gradient descent might get stuck over here, or it will be very slow at this point, right? So that is also again another problem. So in order to solve these problems, some modifications were done on top of our gradient descent, standard gradient descent algorithm, and that's what we are going to study next. Now, the problem with gradient descent, there are multiple problems with gradient descent. So if I come over here, see these two loss functions with respect to some parameter theta. Now over here, one thing is that if when I come towards the lower side, my slope value will be smaller, right? My value of slope will be smaller. So you remember this equation, we have some learning rate times dl by d theta, right? So if the slope is smaller, the update will be smaller, right? So here, let's say here, from here to here, it jumped like this, then it jumped like this, then it jumped like this, then it jumped like this. But here, because the slopes are getting smaller and smaller, the jumps will be smaller and smaller. So it will take much more steps. So it will take more time to go to the optimal minima, that is slower convergence, right? We want faster convergence. This is one problem. So here in this example, we had only one minima. So it's called convex. This curve is called convex curve. Here we have more than one minima, right? And this is known as non-convex. In general, real world scenarios, you will not get this type of loss function with respect to theta. You will actually get this kind of loss function. Alright. So see over here, one thing is that if I started from here, I might get stuck at this local minima. This is one problem, right? So local minima is one problem, and I will basically never be able to reach my global minima. The second thing is that, let's say I was somewhere over here. So this part, if you see in this direction, it is going downwards, but if you see in this direction, it is actually going upwards. Here the slope will be 0. So here also the update might not happen actually, and you will get stuck somewhere here. It's neither local minima nor global minima. So these are known as saddle points, the points that we discussed before also. So your standard gradient descent might feel stuck over here. So what if I try to come up with another optimization algorithm that somehow gives me an ability to actually overshoot local minima? So for example, in this case, let's say I was somewhere over here. Here my slope will actually be 0, right? But if I also take into account that before this I was actually going down and down and down, right? And if I take that accumulation also into account, past velocity, right? If you remember, if I drop a ball from here, it will not be stuck over here. It will actually overshoot this part, right? So in order to do this, why it overshoots? Because it gets up something called momentum, right? So the same concept has been from the physics has actually been used in gradient descent also to come up with a new version known as SGD with momentum. where we also take into account that, oh, previously I was moving down and down, right? So that gradient accumulation, we have to somehow accumulate the past gradients also. And there comes the concept of SGD with momentum, where we are also taking into account the previous gradients. By gradients, I mean the slopes. So if I knew the previous slopes, if I was storing the previous slopes, I would somehow, when I'm making the movement over here, because from upwards, I know I'm going down, 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 I'll still make a larger change, right? I'll still make a larger change. So the speed will be faster. And if the speed is faster at the bottom, there is a chance that I will overshoot this minima. And if I reach somewhere over here, I'll again go down and down, right? So it will also help us in tackling these two challenges also, and also increasing the convergence speed. By convergence, I mean reaching the global mean. All right. Here comes the concept of SGD with momentum. It adds inertia to the updates in order to accelerate the convergence. So if you see over here, SGD versus momentum, SGD is in red. So SGD will actually start making, it is coming over here. If you see, it is taking into account, it is going slow actually. And momentum has actually, because it was storing the previous velocities and momentum, right? So it makes much larger changes, and it has actually overshot it, but it came down, right? So the speed actually accelerates when you use this momentum. All right. So the equation for SGD with momentum is that we have two equations now. One is for calculation of velocity, and the second one is actually for the weight update. So let's come over here. So velocity at time t is equals to gamma times previous velocity plus dl by d theta. If you compare it with a standard gradient descent, the theta nu was theta old minus gamma, the learning rate. This is learning rate, right? And here also we'll have some learning rate. Let's call this that alpha, right? Over here it is written as eta, right? So let's use that same symbol eta over here also. So gamma times Vt minus 1 plus eta times dl by d theta. So Vt minus 1, this is past velocity, previous velocity, and this term eta times dl by d theta is actually coming from our standard gradient descent. So here I'll also use eta. All right. So what is actually being done over here is we have some new parameter gamma that is between 0 to 1, and we are saying that current velocity is some previous velocity plus the learning rate times the current slope or current gradient, right? And then we are using it to update our weights, right? So how does it accumulate the previous gradients? To see that into equation, mathematically actually, so we can come over here. I have not used learning rate over here, but you can use learning rate also, because ideally there is a learning rate. But to illustrate the fact that we are actually accumulating past gradients, what I have done is, let's say I am at P1 point, P2 point, P3 point and P4 point. I was moving through these points, okay? So velocity at point 4 will be equal to gamma times the velocity at point 3, Vt minus 1 plus dl by d theta 4, right? Because I am at P4, here the parameter is theta 4, right? I am trying to get the best values for theta somewhere over here. Similarly, velocity at point 3 will be equal to gamma times velocity at point 2 plus dl by d theta 3. Similarly V2, similarly V1. Now at V1, I will not have, like when I was at this point, right? I don't have any previous velocities, right? So I have assumed V0 as 0. Now what I'm doing is I'm using the value of, this value V3 in equation V4. Alright, so V4 will be equal to this So I have basically replaced V3's value with this value, right, from equation 2, and I get something like this. So now I have got V4 and V2. So now V2's value I am getting from equation 3, and I get this value. So V4 equals to gamma cube V1 plus gamma square dl by d theta 2 plus gamma times dl by d theta 3 plus dl by d theta 4, right? And now I have V1, so I'll use V1's value from equation 4, and V0 is actually 0, right? So in short, if I solve this, you can write it, use pen and paper, try to solve it. You'll get something like this equation. So velocity at 4 is actually coming out to be gamma cube times dl by d theta 1, gamma square times dl by d theta 2 plus gamma times dl by d theta 3 plus gamma plus dl by d theta 4. Now you can, gamma is a small number between 0 to 1. Now if gamma was 0.1, gamma square will be 0.01, gamma cube will be even smaller. So don't you think the V4 will actually give the highest weightage to current slope plus some small weightage to just one timestamp back plus small weightage to even smaller weightage to 2 timestamp back, and so on, right? Here I have done till 4 timestamps. So this is actually known as exponentially weighted moving average. So we are getting average, right? Average of all the slopes, but it is weighted. So the most recent one is actually given the highest weightage. And also you will, if you use the learning rate also, so you will have learning rate also throughout, right? So I can multiply it with eta, right? This becomes my new velocity, and my new update will be influenced by my past updates also. That's what happens when we modify our standard gradient descent to gradient descent with momentum, right? So if I was moving like from here to here, then from here to here, then from here to here, the next time, because I am adding more and more past gradients, the jump will be even higher, right? That is the reason if I was, let's say, starting from here, I jumped like this, I jumped like this, right? I jumped like this, then I might jump further ahead and thereby possibly overshooting my minima. Same thing will happen for saddle point. Even though here the slope is 0, but because I had some past accumulated gradients, I will overshoot this part also, and thereby there is a much higher chance that I will reach the global, right? So this is what HGD with momentum helps us in doing. Alright, now let me show you this GIF. So here the purple color is actually momentum and the blue one is actually the standard gradient descent. So if you see, when both the balls are dropped, the purple one actually reaches the minima. This is actually global minima, this is actually local minima, right? This actually reaches the global minima faster, and the blue one actually reaches the global minima local minima. It gets actually stuck in local minima, and that too it takes some more, like the number of steps are also higher, right? So it is actually solving those saddle point and local minima problems. Now the one problem with HGD with momentum is that if you see over here, once it reaches the minima, it oscillates around the minima. So there is some steps extra required, right? So it's not the fastest still. There is still some improvements that we can do, right? So that's where we'll come up with other such algorithms. So the next one is known as Nesterov accelerated gradient. So Nesterov accelerated gradient actually takes in, you can think of it like this, that it takes into account that what will be the gradient in the future also. So if you see these two curves, right? So this is blue one is pure momentum, and the green one is NAG. So NAG actually is looking that, okay, if I make a step forward, will the slope still be in the same direction or not? That's why the equation, if you see, it is gamma times Vt minus 1 plus learning rate times the slope of the loss when I am actually making that move. Theta minus gamma times Vt minus 1. Theta minus gamma times Vt minus 1 was the previous movement, right? So it is actually anticipating the direction by looking into the future also. So that's why it results in the faster convergence, and that oscillation that happens in momentum, that actually gets reduced. So it's much better compared to a previous algorithm. So we were talking about NAG, right? So let me give a more in-depth explanation around NAG. So let's look at one level deeper. So here I have the formula for SGD with momentum. So SGD with momentum, we have two things. First, we calculate the momentum, that is like the past velocity plus the current learning rate, and then we update the weights, theta minus Vt. So if I use this Vt over here, the formula comes out to be something like this, right? So if I want to explain it in a much more deeper way, so let's try to draw a curve, right? And let's say I am over here, something like this. So let's say that I was at this point, right? And I want to update my theta value. So this is my theta new and this is my theta old. So theta old, there are two components that will basically affect the theta, right? Over here, obviously this value will be negative, right? Past velocity, basically the slope will be positive, not negative. This is positive slope, right? So I have two things. One is the velocity, the past accumulated velocity, right? So past accumulated velocity Vt minus 1, and another is dl by d theta, that is current slope, right? So both are actually going downwards, right? Both are all saying that, okay, move downwards. So the movement will be combination of both of them. So it will, let's say here it was this small arrow, here this was this small arrow, so I got a bigger arrow, right? So the challenge that actually happens is that when you reach somewhere over here, right, past velocity was like this and current slope is something like this, so I make a larger movement, and that's the reason we get those oscillations around the minima. If you remember that this curve that I showed you, right? We had the oscillation around minima in momentum, right? So what NEG does, or Nesterov accelerated gradient does, is it tries to dampen the effect of these oscillations. There is a dampening factor, right? So let's come to NAG's formula. So NAG's formula is that we first calculate velocity, same as the way velocity was calculated, that is gamma times the previous velocity plus learning rate times, but here the slope calculation is a bit different. So let me improve this. So it is d by d theta loss at theta minus gamma Vt minus 1. So there is a bit of difference, and then we get theta equals to theta minus Vt. So let me take that same example. So let's say I was at this point, right? So first thing is, again I'll update the theta with respect to subtracting the Vt over here. So let's assume that velocity accumulated till now was something like this. All right, this is my Vt minus 1. So it's saying go down. But this term here, instead of getting the slope at this point itself, we are saying get the slope at theta minus gamma times Vt minus 1. theta minus gamma times Vt minus 1 means what? This is my Vt minus 1, correct? This is my Vt minus 1. I am saying update the, I want to get the rate of change of slope at a point theta minus Vt minus 1. So theta is over here and Vt minus 1 is saying go downwards. So maybe Vt minus 1 comes over here. Theta minus Vt minus 1 comes over here, this point. This point, theta minus gamma times Vt minus 1, right? And get the slope at this point. At this point, the slope is actually, let's say, a small negative, right? So this term is this positive, basically saying that it's a positive slope and a large number. Here it is saying it's actually a negative slope, right, over here, and a small number. So instead of, when I make the change theta minus Vt, right, instead of making that larger jump, because there is an opposing force over here, I will make a slightly smaller jump. This is the dampening effect of NAG, and in this way the number of oscillations actually gets reduced, right? So this is much more better compared to a standard SGD with momentum. Here instead of calculating both, here we were calculating both at this point, the velocity, I was using past velocity plus the slope at this same point, right? Slope at this point I was calculating. But in NAG, instead of calculating slope here, I first use the past velocity to make the movement forward, get the slope at that point, right? And then combine the past velocity plus the slope at that point. And if I was actually, if there was an opposing force in future, I will take that opposing force in future to dampen the impact of movement that I have. So this is the beauty of energy. Now till now, whatever optimizers we saw, they were more focused around how to speed up the convergence. But they all have one thing in common, that is the learning rate for each weight actually is same. Now that is a problem. There are a lot of cases where you would basically want your learning rates to be different for different weights. Maybe different dimensions have different scale, right? And their slope might be quite different with each other. Having the same learning rate actually creates issues in convergence in those scenarios. So the next step is ADA grade. So it is also known as adaptive gradient. So it is used to have different learning rates for different parameters. So let's come to what is ADA grade. So ADA grade basically adapts the learning rate with the parameters. So this is the first time where different parameters will have different learning rates, and the learning rate will be inversely proportional to the past gradients. So if you had a lot of past gradients, the value was very high, so the learning rate will be low. If your past gradients, the value was low, the learning rate will be higher. So this is very helpful in NLP sort of task, because in NLP a lot of times your features are actually presence or absence of words. So a lot of times you have a lot of absence of words or zeros, right? So in those sort of scenarios, adaptive gradient actually is very useful. So here the formula over here, you can see it over here, but I'll try to give you a better explanation for this formula. So let's come over here. So in adaptive gradient, we have two things. So one is parameter update, and the first thing is actually the grade accumulation of gradients. So here the GT is equals to the accumulated gradient at current time step is equal to previous accumulated gradient plus the square of our gradient. So basically the current gradient, so current gradient was dl by d theta, you square it. Why do we square it? Because the slope can be positive or negative, right? So we are actually, we are not bothered about the sign, we are more bothered about whether the scale was larger or smaller. So that's why we square it. someone can say that if I wanted to add something, I could have taken the mod also. But the problem with mod is that at the end of the day, we will be using differentiation, right? And modulus operation, it is not differentiable at all, each and every point. So that's why we squared it. So we get this GT. Now theta is equals to theta minus the learning rate divided by square root of GT plus epsilon dot GT. GT is basically the rate of change. So if you compare it with standard gradient descent, so my standard gradient descent was what? Theta minus learning rate times dl by d theta. I could have written it like this also. Theta is equals to theta minus learning rate times gt. Gt is actually dl by d theta. Right. So if you see the difference actually comes in this part, and this is the modified learning rate. So this is the modified learning rate. Now, if your past accumulated gradients were smaller, right? That is, the slope was smaller in past, right? This term will be smaller. So your learning rate will be larger, right? But if your past accumulated gradients were larger, right, then this number in the denominator will be large and your learning rate will actually reduce. So in this way, we can have different learning rates for different parameters, right? Epsilon over here is a very small number like 0.00001, and it is used only for the fact that it could be possible, right, that this GT term becomes 0. And if GT becomes 0, this term will tend to infinity, right? That will not help us in training it. The gradient is actually exploding. So that is the reason we have this small epsilon term, that is a very small positive number. So in this way, we can actually adapt our gradients or adapt our learning rates. Now, there is one major problem with AIDA grad. The major problem with AIDA grad is that when you keep on doing this, weight updation, and since you are continuously adding up the past gradients, this number will eventually become larger and larger with every time step. And if this number becomes larger and larger with every time step, right, here you see we are not doing weighted average, we are basically summing up all the gradients, square of all the gradients. So it is GT square is always positive, right? So I am adding positive numbers a lot of times, the number is going to be very, very large. This will make my learning rate at later points of time almost tending to 0. So after a certain time, the update will not take place, right? And we will not be able to reach the minimum. This is the problem with our AIDA grad. All right. So with increase in time steps, my learning rate will tend to 0. That is a very big problem with AIDA grads. So, but learning rate shrinks too much over time. All right. And we might never be able to reach the minimum. So how do we solve this? To solve this, something like RMS prop comes into picture. If you see this equation, instead of adding the square of the gradients, we are also having this weighted average thing. So current GT, think of it like GT only, that we were calculating, is equal to gamma times past GT plus 1 minus gamma times the current slope square. So this is actually something similar to what we had in momentum, where the most recent weight slopes will actually be given more importance, and we'll tend to forget like very far up back in time weights slopes, right? So this actually helps in fixing the AIDA grad's decay problem. Now, can we combine momentum and RMS prop? Because RMS prop is basically updated version of AIDA grad, and AIDA grad at the end of the day was focusing more on what? It was focusing more on adaptive learning. So RMS prop also focuses on adaptive learning, but they are RMS prop and AdaGrad, they are not taking into account the momentum concept, right? So what if we combine the learnings from momentum and the learnings from RMS prop? If we combine both of them, then we come up with a very efficient optimizer that is known as ADAM. We studied about SGD with momentum, we studied about NAG, then we studied about RMS prop, right? And then we studied about AdaGrad and then RMS prop. Now this SGD with momentum and NAG, if you see, they are actually more focused around taking into account how fast we converge, right? Using the basically momentum concept, right? Velocity concept. And AdaGrad and RMS prop are actually trying to improve convergence, but by adjusting our learning rate. So what if we combine the best of both and come up with a new optimizer that takes into account momentum as well as the learning rate adjustment? There comes something called ADAM that is actually used in real world deep learning scenarios. Okay, this is more common algorithm and famous algorithm that we use generally. So ADAM basically stands for adaptive moment estimation, and it is actually combining the concepts of momentum and RMS prop, all right, which is more adaptive, smooth and reliable. So here if you see, there are basically couple of calculations that we do, but if you have gone through the previous algorithms, it is much more easier. So we have two things. One is momentum, that is again a weighted average, right? So past momentum beta 1 plus 1 minus beta times the current slope. Then there is something called VT. VT over here is actually something like that square of gradients that we calculated in RMS prop. So it is also weighted average of past VT minus 1 plus 1 minus beta 2 times the current slopes square. This is going to be helpful in adjusting the learning rate. Now here we also have something called, we are after calculating momentum and the parameter that will be used for adjusting the learning rate VT, we have to adjust their values for this third step is actually known as bias correction. So we'll not go into the depth of this, but the reason for bias correction is that initially we will not have any values for momentum and velocity VT, right? So they both will be actually having values of 0. So in order to adjust for that, what is being done is that m hat t is calculated, that is mt upon 1 minus beta 1 to the power t. T is basically how many time steps we have used, right? Or we can say how many epochs are done. Same thing we'll do for v hat t. It will be vt upon 1 minus beta 2 time beta 2 to the power t. And then again, this is the standard formula. The new parameter is equals to previous value minus the learning rate times under root of v hat t plus epsilon. So this epsilon is also under the part of under root only into the m hat t. So here we have actually taken the momentum concept also plus the RMS props concept of changing the learning rate and came up with ADAM. So if you have understood the previous lectures, you will be able to understand this also. Now there is a variety of ADAM called ADAM W, so which has a slight change that here you also have lambda times theta added. It is actually like a L2 it is like a regularization, but ADAM and ADAM W are almost, I would say, same. Now there are a lot of other concepts also, that is learning rate schedulers. There are different types of schedulers that are available in standard Python packages. So you can modify the learning rate during training for better convergence. So there are various type of decay rules. So step decay, exponential decay, cosine annealing, warm restarts, cyclical learning rate. All right, I'll not go into the depth of these. They are not so like common concepts around interviews. So let's talk about the optimizer summary. So obviously Adam and Adam W are the best. SGD, the memory requirement is low. It is not adaptive learning rate, right? Standard stochastic gradient descent. It does not have support momentum also. Very simple models, if you have, you can use it. SGD with momentum, memory requirement is low. Adaptive learning rate, no, but it has momentum. AdaGrad, high memory. Adaptive learning rate, no momentum. RMS prop, medium memory. Adaptive learning rate, yes, no momentum. Adam, obviously high memory. It supports adaptive learning rate and it also supports momentum, and it is the default choice. And Adam W is actually more common in the transformers part. So what are loss functions? Think of loss functions as a way to guide our model. So if our actual value, the real value and the predicted value are very close to each other, the value of that loss function should be low. And if our actual and predicted value is very far from each other, then the value should be high, indicating that we are predicting very badly, right? So you can think of loss functions as a measure of the difference between predicted and actual value. So it is basically used to guide the model on how wrong it is. And if you remember, we use optimizers to actually adjust the weights of a neural network. So the optimizers actually use these losses, right? We calculate the losses. And if the loss is very high, it will try to adjust the weights and biases of a neural network in such a way that the losses tend to reduce. So let's see what are the different types of loss functions. So there are various types of loss functions in neural networks. Mean squared error, mean absolute error, then there is Huber loss, binary cross entropy, categorical cross entropy, sparse categorical cross entropy, KL divergence, and contrastive loss. So let's come over here. See, why do we have different types of loss functions? The reason for different types of loss functions is that the problem statement is different. So I have taken two examples over here. Let's say we have some binary classification problem. By binary classification problem, I basically mean that your target values, there are only two types of target values. Either it is 0 or it is 1. Let's say 0 stands for cat and 1 stands for dog. You have two classes, right? So here, if I just do the subtraction, that y is actual value over here 1 and y hat is the predicted value, that is 0. If I just calculate the difference, right, it might not be very ideal for training our deep neural networks. So this is an example of classification problem. We want to have a loss function for classification problem. Then there is regression problem. By regression I mean you're basically trying to predict some continuous value. By continuous value, you can see over here that let's say there is some features x1, x2, x3 and y is basically in rupees. The target is in rupees. So actual was 200 rupees and we predicted 210, right? So how do we find out how good or bad it is? Next example, we have 300 as the actual value and 250 is the target, right? So we are underestimating in this example, right? In first case, we are actually overestimating. So here we'll try to have a different loss function, right? So let's come back over here. So one loss function that is quite famous is known as mean squared error. Mean squared error is used when we are solving regression problems. So if you see, this is the curve that we get in case of mean squared error. Mean squared error is nothing but you have actual value and you have predicted value. You take the difference between them and you square it. That is what is mean squared error. So mean squared error because it is squared, right? It gives like a parabola sort of shape. It is very smooth. It is differentiable. But the problem with mean squared error is because you are squaring the difference between actual and predicted, right? If the difference is very huge, and you if the difference is very huge and you're squaring it also, right? So the impact is more, right? It becomes even larger number. So mean squared error, if your data has outlier values are very extreme values. Their difference will be quite large, and when you square it, the impact gets amplified. So mean squared error, in case of outliers, it will give more focus to the outliers. That is one problem with mean squared error. So how do you solve the problem of outliers? Here comes another error or loss that is known as mean absolute error. So if you see, the red line is actually MAE over it. So it treats all errors equally, right? But it is better for outliers if your data has outliers. But the problem with mean absolute error is you can see that it becomes non-differentiable close to zero actually, right? Because it's the mod, right? Mod of x function. And why differentiability is important? Because in optimizers or gradient descent, we are actually doing what? We are differentiating the loss. And if it becomes non-differentiable, then we have a problem, right? Although, just for FII, in case of non-differentiable, there is a concept called subgradients that is used to get the gradients actually. But it is much more computationally expensive. So, to solve this problem, another sort of uh, hybrid of these two losses came into picture, that is actually known as Huber loss. So, Huber loss is actually combining the mean squared error and mean absolute error. So, if the mean squared error and mean absolute error, the modulus is less than some number, we use our mean squared error loss. And if it is a larger thing, that basically means it is potentially an outlier, then we use a different formula. So it actually solves the non-differentiability of mean absolute error towards zero. So closer to the when the difference is zero between the two, it actually behaves like a mean squared error function, and if it is towards the extreme sides, it behaves like a mean absolute error function, such that so that we don't focus more on the outliers. So it gives us best of both worlds. Now, another problem statement comes is when we have categorical data, right? So, for example, this one. So here we have zeros and ones as our output, right? Actual values 1 or 0. 1 could be cat, 0 could be dog, or vice versa, right? So this is a binary classification problem. In case of classification problems, we don't use mean absolute error or mean squared error. Those are used in regression problems. What we do instead is that we use something called cross entropy loss. So if you have only two classes in your data, right? So this example, right? So in this scenario, we use something called binary cross entropy. So here is the formula for binary cross entropy. Here y is your actual value, and y hat is your target value, or not target value, sorry, it is predicted value, right? So it's the predicted value, right? So here, see this example. So here y actual value is 1 and predicted value is 0, right? So let's see if I put actual value y as 1 and predicted value y hat as 0, what is the value of the loss, right? So loss is minus of y is 1 log of y hat, so y hat is 0, plus 1 minus 1, 1 minus 1, right, y is 1, right, log 1 minus y hat, that is 0. So this comes out to be log of 0, right? Log of 0 is what? Here the base is actually, it can be, you can take any base, 2 or 10. So base is greater than 1. So when base is greater than 1 for a log function, the curve is something like this. And if you see, log of 0 is what? Minus infinity, right? So here this value minus 1 into it, this is minus infinity. Minus infinity, think of minus infinity is a very large negative number. Plus 1 minus 1 is what? 0. Log of 1 minus 0 is 1. So you see one thing, when my y is actually 1, when my actual value is 1, this term will always be 0, right? Because 1 minus 1 becomes 0. So this part, when your y is 1, this part does not contribute, right? So you can break this loss also into two parts actually. You can think of loss as minus of y log y hat when your y is equals to 1, right? And if y is equals to 1, you can cancel this part also, right? Y is 1, because it is a binary classification problem. You will always have either 1 or 0. And minus of 1 minus y log 1 minus y hat if my y is 0, right? Because if y is 0, right, think of it like this, if y is 0, actual value is 0, this term will actually, this is 0, so this term does not contribute, it will always be 0, right? So this term will not contribute and only this part will contribute. And 1 minus y, I'm saying y is always 0, so 1 minus y will 1 minus 0 will be 1, so I can actually remove this part also. Oh, I removed way too much. Oh, this part. So this is actually an expanded version of this binary cross entropy. So when your y target actual value is 1, it is minus of log y hat, and when your target or actual value is 0, it is log 1 minus y hat, right? Why this function comes into picture? See over here, when I told you, right, when y is 0, y hat is when y is 1 and y hat is 0, I am basically getting something like this. And if you see over here, this basically becomes what? This term is 0, minus minus is plus, so this becomes infinity, right? Minus infinity. Oh, this is not minus 1, right? Here it was plus 1. So this becomes plus infinity. Plus infinity signifies what? That when your actual value is 1 and you're predicting it as 0, the loss is very huge. And optimizers do what? They minimize the loss. So I want to reduce this loss, right? That's the reason this formula comes into picture. You can try it for other cases also. When y is 0 and predicted value is 1, again the output will be infinity, loss will be infinity. Let's take this example. When both are same, right? When both are same, so I am basically saying y is also 1 and y hat is also 1, right? So let's put it in this formula above. So it is, the loss is minus of y log y hat plus 1 minus y log 1 minus y hat, right? So this becomes what? Minus of y is 1, log y hat is also 1, plus 1 minus y. 1 minus y is what? 1 minus 1, log 1 minus, again this y hat, y hat is also 1. So this comes out to be what? Log of 1. What is the value of log of 1? It is 0. So log of 1 is 0. This becomes 0 irrespective of anything over here. And here also you multiply, this becomes 0. So the loss becomes 0. This is the minimum loss that we can have, right? So that is the reason this function, you can try it for 0, 1 and 0, 0 cases also, right? You can try it in this function. So this is known as binary cross entropy. So this is the benefit of binary cross entropy. So this is a graph for, because I told you, right, that formula can be broken down into two parts. When your actual value is 0, when your actual value is 1. So when your actual value is 0, the curve is something like this. And you can see over here, right, when your actual value is also 0 and this P is actually probability, right. Basically what happens is you predict the probability of class 1. You predict the probability of class 1. So if your probability comes out to be, let's say 0.9, right, and your actual value was, probability from the model is 0.9, right, and your actual value y is 1, right, so y is 1, so blue line, right, and your probability is 0.9, so it's somewhere over here, so you get a small loss, right. But instead of this case, if your probability was, let's say 0.1, right, instead of this case, but your actual value was 1 only, so this blue line 0.1 will be somewhere over here, correct, and the loss is higher. We want to go in this direction. On the other hand, if your y is 0, that is its class 0, and your probability came out to be 0.9, think of it like this, probability is 0.9, that basically says it is class 1 or closer to class 1. See this red line, y is 0, so this red line, and probability is 0.9, so this, right, this red curve, not line, sorry, so this red curve. So this basically is saying I have got a huge loss, I want to minimize the loss. So we'll adjust our weight such that this probability value comes out to be closer and closer to 0. So in this way, this binary cross entropy loss works. I hope it is clear. So, and one thing also, that in case of binary cross entropy, right, let me show this neural network. So this is the type of neural network we generally use for binary classification. The final node, final layer will have only one node, and it will give me the probability value, probability of class 1. If probability is very high, then we are saying the prediction is class 1. If the probability is very low, then we are saying the prediction is actually class 0, right. So here you use sigmoid activation function. Remember we studied different sort of activation functions, right. So here we will basically be using sigmoid activation function, okay. Now let's take the other example. When you have more than one class, right. So if you have, let's say 3 classes or 4 classes or 5 classes, then you will not be using binary cross entropy loss. You will be using something known as categorical cross entropy loss. Okay, so here you have summation of yi log yi hat. So let me show the neural network in case of, this is known as multi-class classification. You have more than 2 classes, right? So here you have 3 classes. Let's say that I am trying to predict whether a student will get placed or not, right? So PA is actually giving me probability of yes, PB is actually giving me probability of no, and PC is actually giving me whether maybe, neither yes, neither no. And I have this sort of, so basically I will have 3 nodes or 3 neurons in a final layer. And here we basically use softmax. So each node over here in the final layer will have softmax activation function. Here the final layer node will have sigmoid activation function. Okay. So when you have more than one class, more than 2 classes, we use categorical cross entropy. So categorical cross entropy is, the formula is something like this. Here C is actually the number of classes. how many classes do we have? C over here is number of classes. So here I have given an example that I have, let's say, features like CGPA, IQ. That will be my input nodes, to the neural network, right? So this neural network here, I'll have CGPA, I have IQ, and these nodes will not have anything. We can remove these nodes also, right? And then the target is whether the person gets placed or not. It's yes, no, or maybe. So what we do is, in case of multiple classes, we do something what is known as one hot encoding. So one hot encoding basically converts this placed column, that is actually yes, no, maybe, into a vector where, if you see over here, the first value tells whether it is yes, the second value tells whether it is no, and the third value tells whether it is maybe. So first example, this is first example, right? There might be some CGPA, there might be some IQ value, right? And here it is, the data says it's a yes. So here we are basically saying, okay, this will be 1, rest all will be 0. In second case, it's a no, right? So all the remaining are actually 0 and this is actually 1. Same thing for the third case, right? So here, instead of getting only, in case of binary classification, we got only one probability. But over here, we pass our data and we will get probability values from here, right? And here, let's say the probability was 0.2, or I'll show you this example. There will be some, let's say, probability 0.2, 0.3 and 0.5. So highest probability is for this neuron, right? So we'll say the output is maybe. Okay. Now let's take one example. So actual target, the first example, if you see, the actual target is 100. So I got 100, and my predicted target is 0.2, 0.3, 0.5. Okay, this is the output from the final layer, right? If you remember, softmax activation function is, it is in such a way that the sum of the probabilities of all these three neurons will convert to actually 1, right? So now how do we get the loss? So if you see this formula, it is for all the classes, summation from all the classes I equals to 1 till all number of classes, yi log y hat. So it is basically, I have 3 classes. So it will be y1 log y1 hat minus y2 log y2 hat minus y3 log y3 hat. Because I had 3 classes. Y1 is basically the actual value for class 1. Y2 is actually the actual value for class 2 for this example. And Y3 is the actual value for class 3. Now you get the feeling, right? Why did we do that one hot encoding part? And predicted value is actually the probability values for each classes. So let's put these values. So Y1, let me take minus sign outside. So it is Y1 is 1 log Y1 hat is 0.2 plus Y2 is 0 log 0.3 plus 0 again y3 hat, and y hat 3 is 0.5. So if you see over here, only that class where the actual target was 1, that will only be calculated, rest all will become zeros, right? So this basically becomes log 0.2 and all of that becomes 0. So this will be the error. And if you see from this curve, this is actually for binary, but we can use y equals to 1 case. So y equals to 1, my actual value is 1, but my predicted value was 0.2. So I'll get a higher loss for this, right? So I'll basically get whatever the value of log 0.2 is, right? So in this way, we basically calculate this thing. Okay. I hope this categorical cross entropy is clear. So let me repeat it once more. We convert the targets into one hot encoded, and then for each class we apply the formula. Here we had 3 classes, so we'll have 3 y log y terms, and we'll get a final prediction. So this is for categorical. Now, what about the losses that are used in LLMs? So in LLMs, although when you are doing the prediction or when you're training the or fine tuning the LLMs, the standard losses are used. Basically, this categorical cross entropy loss is used. But there is something called reinforcement learning also during the pre-training phase of LLMs, where when it tries to understand the language, right? When basically it is trained on a huge set of data, right? There are two phases of creating an LLM. One is pre-training and then there is fine-tuning. So during the pre-training phase, there is some concepts of reinforcement learning used. And in that reinforcement learning part, which is basically called reinforcement learning using human feedback, RLHF something, I think, RLHF. In that part actually, KL divergence is used. So KL divergence is basically to compare two probability distributions. And will not go into depth, but you must be aware of that during the reinforcement learning part of LLMs or in variational autoencoders, it's a branch of a bit sophisticated deep neural networks. KL divergence is used. So KL divergence over here is basically to get how close two probability distributions are. So here P and Q are two different probability distributions, where P is the actual distribution and Q is the estimated distribution. And this pi log pi divided by qi is what is actually known as KL divergence. It's called Kullback-Leibler divergence. So if the probability distributions are quite close, the value of KL divergence will be low. If they are very far apart, the value of KL divergence will be higher. Think of it like this: that if I have probability distribution of a fair coin, and I try to get the probability distribution of another fair coin, and I get the KL divergence, the value will be closer and closer to 0. But if I compare the probability distribution of a fair coin with an unfair coin, the value will be higher, because they are two different distributions. Now, what if we have imbalance in classes? It could be possible, right? In your training data, you have a lot of cases for cats and very few cases for dogs. Now, what will happen is your neural network will try to figure out, or it will be more focused. The weights will be adjusted in such a way that it is more focused in identifying the cats, but it will do a lot of mistakes in identification of dogs because it has seen less of those examples. So, in those scenarios, something known as focal loss is used. It is also used in case of image segmentation also. So whenever you have imbalance in classes, right, then focal loss is used. So focal loss, it just, if you see, there is a slight modification. Y log y hat was basically, if you remember, it was part of categorical cross entropy loss, right? And we have added this -1 minus y hat to the power gamma. This basically tries to focus on those examples more which are harder to classify or which are very less in number. So gamma is actually known as focusing parameter. So it will try to also give more focus, right? It's called focal loss. It tries to give more focus to these cases which are, where we are doing a lot more mistakes or where the number of examples is less. So let's sum it up. We have seen mean squared error, mean absolute error, Huber loss, binary cross entropy, categorical cross entropy, KL divergence, and focal loss. So the first three are used for regression cases, right? When your target is actually continuous, right? And we have seen that, okay, which are robust to outliers and what are the pros and cons. Binary cross entropy and categorical cross entropy, and as well as focal loss, they are used in classification settings where you have classes. Where you are not predicting continuous values, where you are trying to predict discrete quantities, right? And in KL divergence, it is basically for comparison of two probability distributions. So how would you choose the loss functions? It's regression. MSE is default. Huber is more robust. MAE if you have outlier. Binary classes, you have binary cross entropy. multiple classes, categorical, and if it's imbalanced, use focal loss. Couple of mistakes that people do: we use MSE for classification, it's a no-no, right? It's for regression. Forgetting to apply softmax or sigmoid in case of classification examples. Not handling the class imbalance. Class imbalance means you have more examples of one class versus other. And ignoring the label encoding format, right? We remember, right? If you have multiple classes, you have to do that one hot encoding, gradient descent and backpropagation. So we have seen gradient descent, but how does the gradient descent apply to each and every weight and bias is what we are going to look into today. Here, this is where actual learning of the neural network starts. So let us get started. So backpropagation. Backpropagation is basically an algorithm that is used to update the weights and biases of a neural network. And it uses the loss that we compute. Right, during the forward pass, we do the prediction and then we compute some loss, right? That loss, its derivative with respect to each weight and bias is basically propagated backwards, and the weights are updated using the gradient descent algorithm. This entire process is known as backpropagation. So it is used with gradient descent to update model parameters, and the core principle states: start from the output layer, propagate the error backwards. So it is basically telling that, okay, if I adjust some weight W, how should I adjust it such that my loss is minimized? That's what the backpropagation thing actually does. So before understanding backpropagation, we need to understand a very core concept that is known as chain rule of differentiation. So if you remember, in the gradient descent function, we had derivatives. So we had to calculate the derivatives, right? Now, how these derivatives are calculated, something very important, that is chain rule is used. So let's come over here. So here, this is an example of backpropagation. So what is basically happening is you have some inputs x1, x2, x3, and you have some random weights initially, right? You do the computation, that is weighted sum plus bias, and then you pass it through some activation, right? And you get the output. Now from this output, this is the predicted output. What we want to do is, we want to calculate how good this predicted output is. So you have studied something called loss, right? We compute the loss. The loss is computed, it gives us a way, or it tells us how good we are doing, right? And based on that loss, we propagate the things backwards. Again, from this to this layer, then back. If there are certain, further more layers, hidden layers, it will get passed backwards, and the weights are getting updated, right? Now, before understanding how this backpropagation works, we need to understand a very important thing that is known as chain rule. So let's say that I have some function that is y is equals to fx, okay? So if I have something like y is a function of x, right, that basically means I can get the derivative of y with respect to x, right? That will be f dash x. Similarly, if x is a function of, let's say, z, some function of z, so I can calculate dx by dz, that will be g dash z. But if I want dy by dz, basically what is the differential of y with respect to z? How can I do that? So in order to do that, what we can do is dy by dz will be equal to, I know dy by dx and I know dx by dz. So if you compute these two, you will actually get dy by dz, and this is known as chain rule. Okay, that's what chain rule is all about. So chain rule works when you have a composite function. So you can write it like this also, right? That y is a function of x and x is a function of z. So y is a function of gz, right? And if I want dy by dz, first I need to differentiate y with respect to this x, right? Because y is a function of x, right? And then I want to differentiate x with respect to z. Okay, let me give you another example. So here I have y is equals to fx, and the real example is y is equals to x square and x is equals to sine z, right? So composite function is basically y is equals to sine z whole square, right? This x is actually sine z, right? So I have replaced x with sine z. So y is a function of sine z whole square. Now if I want to get dy by dz over here, what I can do is, first what I'll do is I'll differentiate this part dy by dx directly. So I got dy by dx equals to 2x. One thing more for this class, you should have those differentiation rules handy. So if you remember, if y is equals to x to the power n, then dy by dx is equals to nx to the power n minus 1. That's what we have applied over here also. So 2x to the power 2 minus 1, that is 1. Right, so I could have done, let me just do this also. So dx square by dx will be equal to 2x to the power 2 minus 1. So it is going to be 2x to the power 1. That's why 2x. Similarly, dx by dz. So x is a function of z sine z. So dx by dz will be cos z. Derivative of sine is cos. Right. So these two I have got. Now what I'll do, I'll apply the chain rule. I want dy by dz, so it will be dy by dx into dx by dz. So I have got 2x into cos z. Now x again is a function of, I want everything in z. Okay. So because I want dy by dz, I'll replace x with z. What's the value in z? So x is basically sine z. So it will be 2 times sine z cos z. So this is my del y by del z. So this is known as chain rule of differentiation. Okay. So that's what means. The chain rule allows us to compute the derivative of a function that is composed of multiple functions. So here, if you see, we had two, like y was a function of x, but x was also a function of something else, another variable, right? So if I want dy by dz, I would you combine these two. So this is known as chain rule of differentiation. So we apply the chain rule to propagate the loss gradient backwards through each layer. All right. Now gradient descent, if you remember, gradient descent was what? If I want to update my some parameter theta, it will be theta equals to the old value minus the learning rate times the derivative of loss with respect to the theta, right? And slowly and steadily, what we will do is by iteratively applying this thing, we'll basically be getting the ideal value of theta where the loss is minimum, right? Since here derivative comes, that's the reason chain rule comes into picture, right? We need to calculate derivatives at each and every step. All right. Now let's take an example. So let's have one network which has two neurons. Okay, two input input values, two neurons, and one output, that is sigmoid. And we'll have ReLU activation function in the hidden loop. So let's take this example. So I have written this down over here. So if you see this network, so I have two inputs x1, x2, right? Here is some weight associated with this, this edge, and there is a weight over here. Then there is a bias for this neuron B1, and here the bias is B2. W1 is the weight for this neuron, W2 is the weight for this neuron. Then the output from here is basically passed to ReLU activation function, and we'll get something A1, the output from this, and A2 is the output from this neuron. That will be again done the weighted sum with W3 and W4, and a bias will be used. And then finally, we'll apply sigmoid activation function to get my y hat. All right. So this is basically a binary classification problem. That's why we have sigmoid activation function. So let me just show you the forward pass equations. So if I show you, well, let's say first we'll have to do weighted sum, right? W1 x1 plus b1. So W1 x1 plus b1. That will give me my z1 value. Z2 will be W2 x2 plus b2. Okay, so that will be passed from here. Now here, after that, ReLU activation will be applied, right? So ReLU activated value will be A1 is equals to, this is also known as pre-activation values. So pre-activation values. Post activation, we will basically apply whatever this value is, that will be passed to this function, right? Relu was basically max of z1 or 0. Same thing will be for the second one. So here a2 will be max of z2 or 0. All right. This is forward pass, right? I am going from input to the final. This is forward. Here updation is not happening. So we are not calculating derivatives over here. Now this A1 and A2 will be passed to this final neuron, right? So here I have basically written, okay, Z3 equals to W3, this is this way, times A1 plus W4 times A2 plus the bias B3. And now this Z3 will be passed to my sigmoid activation function, right? This is basically now before activation, what was the weighted sum. And sigmoid will be y, basically this will give me final prediction, right? So y hat is 1 upon 1 plus e to the power minus z3, right? And whatever is the value of this will always be between 0 to 1. If you remember, sigmoid activation function always gives the value between 0 to 1. So I'll get my prediction, right? Now post this prediction, so this was entire forward pass, right? I initially these w1, b1, w2, b2, all these values will be randomly assigned. Now what is going to happen is, once forward pass happens, right, I have got my y hat. I'll calculate my loss. Since it's a binary classification problem, the loss will be what? Binary cross entropy loss. So that is going to be this minus y log y hat plus 1 minus y log 1 minus y hat. Alright. So this will be my loss compute. And now post this loss, this is the loss equation, right? Post this loss computation, we are going to update the weights. Now how would the weight updation happen? This is where backpropagation comes into picture. See, for gradient descent to work, I need derivative of the loss with respect to the weight, right? So if I want to update W3, so W3 will be W3 old value minus the learning rate times the derivative of loss with respect to W3, alright? Now the challenge over here is, if you see loss is basically having two variables, y and y hat. Now tell me, think about it for some time, which thing can change? Will your y change? Y is your actual value, whether the particular image that we saw right now during forward propagation, is it an image of cat or not, right? That value is fixed, right? Actual value is fixed, right? That is your actual value, you cannot change that. What is the thing that you can change? That is y hat. So loss over here is actually a function of my y hat, right? So loss is a function of y hat, but I want the derivative of loss with respect to W3. How can I get that? So let me show you this. So loss, I have shown it like this, that loss is actually a function of y hat. Now how is y hat dependent on Z3? I want to find out the relation. So if you see over here, loss is a function of y hat. Y hat is actually dependent on Z3 only, right? Post Z3, after we are getting the value of Z3, then only we can get y hat value, right? So I can say y hat is actually dependent on Z3. It's right. If I change this variable Z3, if I change the value of this variable Z3, I can change the value of my y hat, right? So here basically what we are trying to do is we are trying to see that I want to minimize this loss. I can minimize this loss by changing y hat, right? And making it much more closer to my actual y. Now how can I change y hat? Y hat can only be changed by changing Z3 actually, right? Now how can I change Z3? Z3 is actually dependent on three variables, W3, W4 and B3. These are the three parameters, right? A1, A2, you have got the values, right? Computed values, but if you change these parameters W3, W4 and B3, you can actually change Z3, correct? So this is the chain that is being formed. Now, can you see something like this? That loss is a function of y hat. Y hat is actually a function of z3, and z3 is a function of w3 also. Right now I want dl by dw3, right? Now, can you think of this? Don't you think this is something similar to what we saw before, chain rule, right? So if I want derivative of loss with respect to w3, what I can do is derivative of loss with respect to first y hat, because loss is directly dependent on y hat. If you see this equation, loss is directly dependent on y hat. Now, and y hat is actually dependent on z3. Why this equation? Sorry. Y hat is actually dependent on z3. So I can easily compute dy hat by dz3 also. And z3 is actually dependent on w3 via this equation. So I can compute this also, right? So if I compute these three values, I can actually update my w3. Now, do you guys get this, that why chain rule is useful, right? Same thing we'll do for w4 also. So see, for w4 what we'll do is loss is dependent on y hat is dependent on z3. We'll take this path. For b3 we'll take this path and we'll update the parameters. So once I get dl by dw3, everything is done, right? So now let's compute dl by dy hat first, right? That's the first thing, because loss, we can directly see that it is actually a function of y hat. So dl by dy hat, if you see, y over here is actually constant, only y hat is variable, right? We are trying to adjust y hat. Y is constant. If you think y is actually, let's say it was an image classification problem, I passed one image, it was an image of cat, so it is already fixed that it is an image of cat, right? Our predicted output should be image of cat, so that is variable. So y hat over here is variable. So if I differentiate this with respect to y hat, considering y as constant, I'll basically get something like this. So y is constant, log y hat will be 1 by y hat plus 1 minus y is constant, and if I differentiate this, it will be some minus 1 upon 1 minus y hat. You can check, like if you can take a refresher on differentiation, it's quite easy differentiation over here. So I'll just simplify this entire equation and I'll get something like this. So dl by dy hat will be 1 minus y upon 1 minus y hat minus y upon y hat. All right. You can try this differentiation. I think it should work out for you also. All right. So that's what we have done over here also. So dl by dy hat is equals to 1 minus y upon 1 minus y hat minus y upon y hat. So I got dl by dy hat, right? Now the next thing is dy hat by dz3, right? So let's try to do this. So dy hat by dz3 is equals to d by dz3, 1 plus, here sigma was applied, right? 1 upon 1 plus e to the power minus z3. For simplicity's sake, let's assume z3 is z. I don't want to write z3 every time, okay? So dy hat by dz would be d by dz 1 plus e to the power 1 upon 1 plus e to the power minus z. I can write it like this also, right? So till now we have got dl by dy hat, but we want what? We want these two also, correct? Now y with respect to z3, y hat with respect to z3. So y hat is sigmoid of z3. So let's try to differentiate this. So every time I have to write z3, that's why I've assumed z3 is z for ease of our example, right? So the equation becomes something like this. Now this, I can take 1 plus e to the power minus z to the numerator. So this will become minus 1. Now what I can do is, here differentiation rule applies. First initially let's assume this is some variable x. So this will basically become x to the power minus 1. So if you differentiate x to the power minus 1, it basically becomes what? Minus 1 x to the power minus 2. So that's what is written over here. Minus 1, this was x to the power minus 2. and then we differentiate this. What is my x? Again, chain rule is only applied. Here I have split this into two sections. Okay, so I'll not go into depth of this. You can try it on your own also. So this is, if I differentiate this, so this is constant, so it will be 0 plus e to the power minus z will be e to the power minus z, and minus sign is there, that's why minus 1. So this comes out to be something like this. Now this can actually be broken down into two parts. So I have written it into two parts, 1 plus e to the power minus z 2 times and e to the power minus z over it. Okay, this is fine, right? Now this actually 1 plus e to the power minus z is y hat only, right? But what is this thing? This is actually 1 minus y hat. If you do 1 minus y hat, you will actually get the same equation. So that's what is put over here. And I can show you the calculation also over here. Where is it? Oh, here. So if y hat is this, if I do 1 minus y hat, I'll actually get the same, this equation only. So that's why I've written it as 1 minus y hat. So this is the value of dy hat by dz. Alright. So that's what has been put over here also. Dy hat by dz. Okay. So we have got these two values, dl by dy hat and dy hat by dz. The only thing that is left is dz3 by dw3. dz3 by dw3. So z3 is a function of w3, this equation. So when we differentiate this, since we are differentiating with respect to w3, all the other things will actually be considered as constant. So this is w4 is also constant, b3 is also constant. So the derivative of constant is 0, right? So our value will be a1 only. dz3 by dw3 will be a1, right? So we will just multiply all of them, right? And we will get this value, y hat minus y times a1. If you, dz3 by dw3 is a1, right? Now how come y hat minus y, the product of these two actually comes out to be y hat minus y? We have those two derivatives, we can just multiply them. This was dl by dy hat, this part, and this is dy hat by dz3 that we calculated right now. If you multiply these two, you will basically get y hat minus y. And so we will basically be getting the final value dl by dw3. Now same thing, I have now got the value dl by dw3. I have y hat, I have y, I also have value of a1. I will use it to update my w3. Alright. Similarly, I can do the same thing for updating my w4. Same process is applied. Same thing for b3 also. Okay. And this is actually what back propagation does. Similarly, when I want to update w1, I'll again get the equations. Okay, and I'll find out, okay, where what things, L, basically if you see, loss is dependent on y hat is actually dependent on a1, and a1 is actually dependent on w1, right? a1 is dependent on w1. If you see, a1 is actually dependent on z1 and z1 is dependent on w1, correct? So if I want to get the chain of this, what I can say is loss is dependent on y hat is also dependent on, if you see, z3, right? Y hat is dependent on z3. Z3 is actually dependent on a1 also. So if I change a1, z3 will also change. a1 is actually dependent on z1 and z1 is dependent on w1. And right, z1 is dependent on w1 and z1 is also dependent on b1. So now what I have to do is, again chain rule will apply. Here the steps will increase, right? First I want to do dl by dy hat, then dy hat by dz3, then dz3 by a1, da1 by dz1, dz1 by dw1, and then if I want to differentiate with the b1, so I'll do with respect to b1. Alright, you don't need to do the differentiations, but it's important to understand the concept. And chain rule is actually very important, and the properties of derivatives are very important over here. So I hope you guys get this part. Why derivative is used, why chain rule is used over here, right? So here we have basically shown that what calculations will happen in the hidden layer also, right? And what will be the output layer, hidden layer, all the gradient values. And then we'll basically be updating the corresponding weights. You don't need to do these calculations every time, but it's very important to understand. Here we have basically shown the full pack prop thing, all right? And in this way, slowly and steadily, your weights biases will be updating, all right? Now let's see some common derivatives in action. So sigmoid's derivative is this. We have shown this also, right? Sigmoid was basically y hat into 1 minus y. Y hat was basically sigmoid of z. Here they have written sigmoid. Tan h, the derivative is this. ReLU, the derivative is 1 if the input is positive, else it is 0. And leaky ReLU, it is 1 if the input is positive, or alpha if the input is negative. Hyperparameters, that is very important for neural networks. So we have studied parameters, right? Parameters are basically what? They are weights and biases that a neural network learns. So they are automatically learned via the training data. Hyperparameters are those parameters that cannot be learned via the training data. This is what machine learning engineers or data scientists actually optimize. All right, so let us get started. So what if a neural network does not perform as we wanted it to be, right? So what can be done? Here comes the concept of hyperparameters. These are values that are set before training, before the training process, and it controls how the model learns. The hyperparameters cannot be learned from the data. So if we have like right hyperparameters, it will lead to faster convergence, better generalization. And if we do not have correct hyperparameters, it might be overfitting, underfitting, slower learning, right? Or it might even be like we fail to converge. So what are the different categories we can categorize these hyperparameters into? So there are certain hyperparameters like learning rate, optimizer type. Like we have studied different types of optimizers, right? Grade SGD with momentum, and then the Adam and all. Those were optimizer types. Gradient clipping. So there is a situation where it might be the gradients might overflow. So in those situations, like you have way too large gradients, right? So gradient clipping comes into picture. Then scheduler also, learning rate scheduler. When the learning rate should be high, when the learning rate should be low. Then architecture hyperparameter. These are basically hyperparameters that define the architecture of a neural network. Like what are the number of layers, how many units per layer, like how many nodes or neurons per layer, what are the different activation functions in each layer. The next one comes to be regularization hyperparameter. So regularization is used when you are data, when you have situation of overfitting also, right? If you studied linear regression or logistic regression, you had L1 L2 regularization, right? So same regularization also is over here also. There is something extra, that dropout is there. Then you have early stopping. Basically, if you see that your model is overfitting, you stop. You stop training the neural network. Then there are training hyperparameters, batch size. How many batch size is basically how many samples should be passed through the neural network before the gradient update starts taking place. Epochs, how many times you want to pass the data. Data augmentation also. A lot of cases are there, like specifically in image classification or image related tasks, that where you might want to augment your data to make it much more generalizable. So let's deep dive into each of these. So first thing is learning rate, right? If you remember, learning rate was used where? It was used in the gradient descent step. This term, eta term, this is actually learning rate. So if you have a very large number, then your gradient update will be like very fast, right? So it might be possible that you might not even converge also. If it's way too large, it will start, going away from the minima. And if you have very small learning rate, then it might be possible that it takes so many steps, like 300, 400 epochs or thousands of epochs, and it still is not, reaching the minima. So you have to have like a decent number for learning rate. Then optimizer types, we have studied various optimizer types, right? SGD with momentum, Adam, RMS prop, right? So the different optimizers are used, and we have studied it in the previous classes also. What are the pros and cons? Generally, Adam is preferred, and SGD with momentum is also quite preferable. Then batch size. So batch size basically dictates that how many samples should be passed in the forward propagation before backward propagation starts taking place, right? So if you have a very small batch size, then what is going to happen is your gradient updates will be quite noisy. But the benefit of that is that if there is a local minima, because the gradient updates are noisy, it might overshoot the local minima and thereby not get stuck in the local minima. So that's the benefit of small batches. And the second thing is, when you have small batches, you have low memory footprint. So if your RAM or GPU is less, you can have smaller batches. Large batches are basically you have more stable updates. Basically, large batch basically means you're taking a look at a larger chunk of data before doing the step in the gradient descent algorithm. It results in faster training, but the problem with this is it might get stuck in local minima. So it has like a chance of getting stuck in local minima. And the one more thing is that it will require much more memory. Right, typical ranges are from 32 to 512. So 32, let's say 32 basically means if I'm doing some sort of image classification training, I'll pass 32 images first. Using those 32 images, I'll calculate my loss and then I'll update the weights, and this will keep on happening. Number of epochs. One epoch is basically one full pass through the training data, right? So if I had 1000 images, once all the 1000 images have been seen by my neural network, I'll conclude that one epoch is done. So epoch, if you have way too many epochs, it will start overfitting because your model will start memorizing the data. And if you have way too less epochs, then your model will underfit because you have not given it sufficient time to understand the pattern of the data. So there is something called early stopping, which uses the loss on your validation set as an indicator of when to stop. So if you see in this graph, it has gone 1 second. So here we have epoch and loss, and here if you see, loss goes down, and after a certain time your validation loss becomes almost constant. So wherever your validation loss has stopped reducing but your training loss is still going down, you basically say that okay, I'll stop. It might be possible that your training loss still goes down, right, because you're overfitting situation, but on your unseen data your loss actually starts to go upwards, increases, then you'll stop. Dropout is another thing that we use for regularization of our neural networks. So dropout basically does what? It switches off during training process randomly X percentage of the nodes. So if your dropout rate is 0.8, randomly in a layer 80% of the neurons will be switched off during training. So this in turn forces the network to learn alternate paths and not be dependent on some particular set of neurons. It helps in better generalization. If your dropout rate is 0, there will be no dropout, and generally dropout rate is between 0 to 0.2 to 0.5. It forces the network to not rely on specific paths, but and also results in better generalization. Now weight decay. So weight decay, the concept of weight decay comes from regularization. You have studied L1, L2 regularization in linear regression or logistic regression. So here I have loss total That is the loss that we calculate during gradient descent, right? That is basically the loss, the normal loss that we used to calculate. We had seen different loss functions, plus lambda times the weight square. So this is known as L2 regularization, because why L2? Because we are doing weight square, and lambda is the regularization. It basically says that how much importance should be given to this regularization term, right? So if you have a larger lambda, more focus will be given here and less focus over here, and vice versa. So this in turn actually allows your system to prevent overfitting, right? Because if your weights are way too large, this will do what? If your weights are way too large, that basically means you're focusing more on a particular feature, right, or a particular node. It will penalize those larger weights, right? So it is often used in SGD and ADAM. Learning rate scheduler. So if you remember, during the early phases of your training, when you are way far, very far from your local minima, what you will try to do is have larger updates. But when you are closer to the local minima, you will try to have smaller updates, right? So that's what this adapting of learning rate during the training for faster convergence and avoiding getting stuck when the local minima comes into picture. So there are various types of learning rate schedulers. There is step decay, cosine annealing, warm restarts, one cycle, exponential decay. So there are various versions of these learning rates. Then another important concept comes is model depth and width. So if your model is very deep, right, it can learn way more complex things, but it has a chance of overfitting also, right? And it also has a chance of vanishing gradient. Because why vanishing gradient? Because when you do the back propagation, you might have like very small or in decimal the gradients, right? 0.1, 0.2. And if you go backwards and your depth is way too large, so 0.1 into 0.2 into 0.3, very small numbers, when they multiply, they will come closer and closer to zero. So the initial layers, the starting layers, or right, they will not be effectively, the weights will not be updated, right? So we need to figure out what should be the depth, right? So the strategy is to start small and increase gradually and monitor train versus validation loss. So start small. If you see that, okay, my work is done, I'm getting decent results, that's fine. If no, then you increase the complexity. So this is basically how complex the model becomes. Also, the next thing is like, if you have like a very a lot of layers and lot of neurons in each layer, the time it takes to do the prediction also, because the number of calculations are increased, it will also increase, right? Thereby, when you take it into production, the inference time also is very important, right? If you are getting like 1-2 seconds of time for each single example, let's say I was doing image classification, cat versus dog, but it is taking 5 seconds because my network is way too complex. That is also a problem, right? So we want to reduce the number of neurons or complexity of a network. Now let's take a look at some tuning strategies. What should we, how should we tune the strategies? One way is basically to just do manual hyperparameter search. Like you have manually set, let's say, batch size as 32, 30, then 64. You train the model, you get the performance. This is not, it's not systematic. So it is prone to, you might forget what you have tried, what you have not tried, right? So that is a problem. So wherever you got the minimum loss, that is your answer. Another way is to do grid search. You basically you try all the combinations of, let's say I was trying batch size versus learning rate, and whichever I tried all the combinations of batch size versus learning rate, and whichever gave me the best result, that is my answer, right? But again, it's way too complex. Every time you have to train the model, right? Then there is random search, and that is very effective in a lot of cases. So you basically have some set or combination of hyperparameters, and you randomly pick 2-3 combinations, and whichever gives you best result, you pick it up. A lot of times it also happens that you initially have like a very large search sample that of, let's say, batch size and learning rate combination. Let's say you have 100 combinations, and then first you do random search, and then you narrow it down and then do the grid search. That is also an option. Another approach is that you use Bayesian optimization. So Bayesian optimization, it basically sees, okay, where whether what was the past runs, what was the result of past runs, right? Was it improving on increasing the batch size, or was it improving on decreasing the batch size, right? So it is taking some information from the past runs also. That is much more intelligent. Now, what is the recommended tuning order? So first is learning rate, then is batch size, number of players or units, and if you see overfitting, then you use dropout or L2 regularization, and you also then at last try to have activation functions and optimizers and schedulers. And if you are in image cases or you have lack of data, then you might also try data augmentation. It also helps in, if you have lack of data or overfitting situation, then also data augmentation can come into picture. So this is a summary of what are the different hyperparameters, what type is it basically, whether it's for training, regularization, architecture, what is a good preferred range, and what is the effect. For example, dropout rate, basically, if you increase dropout rate, you're basically trying to simplify the model because you're removing the connections during training, and that is actually preventing the overfit.
You've just finished a live deep learning bootcamp. Great job. But this is only the beginning. We've got many more tutorials and live sessions coming your way, all designed to help you grow as an AI ML professional. The more you experiment, the faster you learn. So tell us what you'd like to explore next in the comments. And don't forget to subscribe so you don't miss any updates from Newton School. Keep practicing on Newton School Launchpad. The link is in the description. Well done today. Keep learning, keep building, and we'll see you in the next live.